Hello everyone and welcome to Explosion Effects in Houdini. My name is Saber Jlassi and I'm going to be your instructor for the next 10 weeks. During this workshop, we're going to cover a variety of explosions and learn how to create everything from scratch using Houdini existing tools as well as creating custom tools. We're going to look at two render engines, Mantra and Arnold, and learn how to use them to their most potentials and explore all the features they have to offer, as well as going over the compositing workflow to make the simulation and renders look as good as possible. We're going to base our work on some of the highest quality work out there created by ILM and Weta, and do as best as we can to mimic their result and or get very close to what they have achieved. By going through these various examples, we're going to cover a variety of topics. Each one has its own difficulty, and hopefully by learning how to use Houdini for simulation as well as how to achieve and build the visuals, the student by the end should have a complete understanding and feel very comfortable on how to tackle complex effects, whether it's an explosion or a dust storm or anything related to smoke and simulation in Houdini. We should have a very clear idea on how to tackle these problems as well as build the visuals. A big problem of building visual storytelling with explosion is how to design that, how to put the layers together and how to put the elements together. We're going to talk about a lot of this. We're going to take one of the Emmy nominated shots from ILM from Star Wars, which is the nuclear explosion with the rings. We're going to study that and try to mimic and create something similar. While doing that, we're going to look at the existing workflow and everything that is available and see if we need to extend or develop anything custom to achieve exactly what we want. And we're also going to cover in depth the new workflow on how to composite something like that. The first shot, which is this one, the one with the strikes, this is from Weta work on the latest Avengers, and I will show the reference later, and we're going to try to mimic what they have done and create something similar. Now, Houdini 18, 18.5 and 17.5 has continuously gotten new features that we're going to talk about and see how to use those features in the most efficient way. Houdini 18.5 comes with a lot of new pre-built-in tools that looks very, very promising, and they are very promising, but we don't just want that. We don't want an existing tools, because I can give someone the pre-built file or a final file from something that I have done that includes everything, includes the final result, the HIP file, the compositing. That does not mean that they know how it's been done. And this is the same thing with Houdini OTLs or pre-built workflow. Having something that exists in Houdini, it does not mean that you know how it works. And very, very quickly, we realize that we have to change something or customize it to fit the need, of a specific production or a specific requirement in a shot, and then we are stuck if we don't know how it works. So we're gonna dive deep and go to the lowest level and start building everything and have the tools that we need so that we can easily control them and know how they work. This does not mean we don't want to use existing side effects tools. They are great, but we also want to dive deeper and give you guys the foundation required to feel fully comfortable tackling complex shots and achieving them. So we have a lot to go through, and let's get started. Hey guys, and welcome back. So let's get started. What I wanted to talk about in this video is the content of the workshop, and we're going to dive deeper into the visual and storytelling. So the effects, or the majority of the effects that we're going to be creating, are this and or similar to this. And what we have here is a three styles or three variation of explosions. And the first one is inspired from the work of Weta that they did on the Avengers, and I'm going to show the real reference, and we're going to take a look at that in more details later. And then these are individual explosions. This could be a mid-scale explosion and or a large-scale explosion, depending on how you wanted to tweak it. It also contains multiple impacts, multiple sourcing, and we're going to implement a lot of techniques to add details. The last one, the big one, is the nuclear explosion. And this one is combined of multiple elements, not just the core explosion. And we're going to focus a lot on building the visual, because the explosion by itself is only a portion of the screen, is only a portion of the effects, but getting all of that to look similar to what ILM did in Star Wars is going to be the real challenge, to getting that same look, which involves a lot of artists combined. So when we see something in movies, it's not necessarily, or it's not guaranteed. When we see something in movies, it's not guaranteed that when we see something in movies, we generally assume that it's an effects work, or when we see an effects shot, we just assume that the effects person or the effects team did that. It's not true. It's actually far from true. What the effects artist did is they created the actual simulation and or the destruction. In many cases, the effects team also does the rendering, but there's a lot of iteration over that, and they work in collaboration with the lighting team as well as the compositing and the supervisor. So for example, in a shot like this, in the nuclear explosion shot, what happens is they start with concept. They have an artist who is probably a senior or a lead artist with 10 to 15 years of experience, who will start doing visual research. With these visual research, they will narrow down the how the explosion is going to look like, how big it is in the frame, how the contrast, the colors, all of these things, they can be quickly iterated on by a concept artist. This part I personally don't have. I don't have a concept artist. I'm not a concept artist. So I'm going to do all of this research in Houdini and or in Nuke on top of my renders. The other thing is, this concept artist is not working, or she's not working by herself or by himself. They're working with another team who will give them feedback. So it would be the director or the supervisor. So there's a lot of art research that happened before getting that awesome explosion or the wow effect. Then we have the cinematographer, we have the compositing guys, we have the sound effects, we have all these elements that gets poured into one shot or one sequence, and then that all of that combined gives the final result and the wow effect. The effects person only did one portion, but in this case, because I have and my team has a variety of experience, a vast experience, and we've done compositing, we've done lighting, we've done everything, we were able to basically replicate everything that ILM team was able to achieve, and we're going to share everything with you guys. So when we see an explosion, when we see an effects shot, please account that there is a lot of work that went into creating that, and creating the visual, and creating the camera, and creating the story. All of it combined creates the wow effect. And the explosion is generally one part of the shot. Okay, so that's something I wanted to talk about. Okay, so now I wanted to talk about this shot, and then the nuclear explosion, which we'll do in the next video. Thank you guys for watching, and see you in a bit. Hello everyone, and welcome back. This video contains a spoiler from the Avengers Endgame movie, and just be aware, if you haven't watched it and you want to watch it, you probably don't want to see this sequence or this effects. What I'm going to talk about here is basically the reference that we used to create the Avengers explosion, the Weta explosions from the Avengers movie, and this is the sequence. Again, you can skip this video, you don't have to watch it, the effects are already explained. And this is the reference that we used. So basically, this spikes like explosion with multiple layers, and we analyze this. We will analyze it together and see what they're built of. And I've read the PDF. They have a PDF about their own combustion model, which is brand new inside of Houdini. I don't think it's a custom solver. I think it's just a combustion model inside of Houdini that they built. And then they designed a whole animation system where they could have artists plug in inputs, basically place and time the explosions, and then they will run it through the system that will digest that and create sims. So I think our end result is very similar, and if we get to 80% or 60% of what Weta can do, then we have achieved a huge milestone, because there is so many other factors, as I explained, that goes into creating this. So it's not just the tools. And I think by the end of this workshop, I feel that everyone should be able to achieve and look at something from existing movies or from a pitch or something, and design and create effects that will hopefully satisfy that visual and look really, really good. So this is a reference, and we'll talk about it in the next upcoming week. So the idea for this workshop is we're going to start the week one by fully understanding how Houdini works and get everybody to the same level. And it is designed for beginners as well as existing users or existing students who took previous workshops. And I'm going to explain our workflow and how we sim and how we wedge things and how we test things. And then I'm gonna explain in depth how the new combustion model works and what we're going to be doing over the next 10 weeks. So this is a reference, and you guys can check it out. You can Google Weta. I'll probably send the link. Weta Avengers Breakdown, and you will find this one. Cool. Thank you guys for watching, and see you in the next video. Bye bye. So the next big studio is probably ILM, and they have some of the best explosions. And one of my personal favorite shot is the Jeddah destruction. And again, this is the spoiler from Rogue One movie. If you haven't seen it, you probably can skip this because we're going to be creating the explosion. And this is the shot that we tried to replicate. So this is the explosion. There's a beam, or there's a beam hitting the ground, and then we have all these nice rings and explosions. And as I was saying, there's a lot of research. There's a lot of concept art that went into creating this, and to make it look as good as ILM, concept art is a huge challenge by itself, let alone creating the effects. So if we get to 80% close to what ILM did, then I think we have a very good starting point. So we're gonna try to recreate something similar. We're gonna customize the solver to give us the look and the feel that we want, and we're gonna do a lot of visual research. So this will be covered in the second half of the workshop. And our idea is we're gonna explain Houdini, as I said, go over Weta example, and then various other explosion types, and then the nuclear explosion. And each one of them, we're going to use a different render. So we're going to cover Mantra, and we're going to cover Nuke. And by the end, if we get you guys to become really comfortable creating explosion, rendering them, doing visual research in Nuke, then we have achieved the goal, and that would be a huge achievement, and that's what we're looking to accomplish. So this is the reference, and we'll study it more later once we start building the effects. Thank you guys for watching, and see you in the next video. Bye bye. Hello everyone, and welcome back. Another important thing that we should consider and learn is how to create explosions without using simulations. And this is something rarely talked about and rarely explained, and we need to learn how to use Houdini in all its tools, whether it's a sim or fake or anything really, as long as we can achieve the visual. And I wanted to show one of the effects that I did for this studio called Barnstorm VFX, and they do some amazing stuff. They did a lot of, almost all the stuff for all the effects, visual effects for the Man on the High Castle TV show, and this demo reel contains some spoilers, so if you want to watch the TV show, that's perfectly fine. I'm gonna show a nuclear explosion that is not done based on a sim, or done based on a sim and procedurals. And let me find it. So this is the shot, and this is the nuclear explosion. You can see a ring and then some dust from the mountains and from the ground. So the way I've done this is, well, obviously, like you would start in every show or every R&D, you want to get this to look based on a sim. So, and I started doing that. I started doing sims. I tried to get that nice billowy, and they had this reference that I needed to match it close as possible. And after a couple of days, I knew that that path is not going to lead anywhere. So I resorted to something else. And the reference for this nuclear is a very famous reference where you have this ring billowing, and there is like a fine line inside the explosion that is emitting light or basically temperature and heat. And then you have this layer around the explosion that is evolving. And what I've done is, instead of doing sims for this, I basically created it based on various elements. So this column here is a procedural tube that I modeled and added noise, and I'm just moving the noise upward. Then I used it to slowly emit smoke to give it that, the advection feeling, as if it's a smoke sim. I mean, it is a smoke sim, but the idea behind it is to give it that realism feeling, and as if it's evolving. This bottom ground is a separate sim. So this one I created a lot of, I created a sim, and then I used one of the frames, duplicated the frame multiple times, and I simply filled the ground around it, and then I let that fall down. So because this was a specific shot, when we cut into it, we want to see that effects right away. So I had to design everything that looks perfect for this. For this one, it's a fully procedural thing. There's no sim. So I modeled the shape of the geometry. I used NURBS surfaces, and then I converted the NURBS surfaces into a volume, but made sure that I have a UV coordinate, and that UV coordinate allowed me to move a noise pattern, and I used it to add some distortion, some noise, and that gave me the revolve feature. And then I created something similar with a ring, with basically a line inside of it, and that line is also evolving and rolling. And by combining all of these and building the fields by hand, I was able to get the look that I needed. So you don't have to always do sims. You can achieve a lot of things without doing sims. And then these mountains, each one of them is a separate sim. And then the ground is a sim, obviously. The sim was way longer. It actually reached all the way up here, but they ended up cutting it. So what I'm trying to say is, not everything has to be sim. If you wanted to actually sim this and get this billowy effect, it would probably be really slow and really hard to achieve. And I want to talk about this maybe at the end of the workshop. I want to show how we can do some of these effects as well. So that's another thing I wanted to talk about. Thank you guys for watching, and see you in the next video. Hello everyone, and welcome back. In this video, I wanted to talk about the prerequisites for new students and what you should know before starting learning this workshop. We are going to be quickly ramping up the complexity and start diving into really complex topics in Houdini and just getting stuff done. If you have never used Houdini, or if you have spent a couple of weeks playing with it, it's going to be really hard for you to follow along, and you're going to get frustrated very, very quickly. This workshop is designed based on the Introduction to Houdini for FX Artist workshop. So everything we build, everything we designed, we account for our students to have already taken the Introduction to Houdini for FX Artist, or they are already very comfortable using Houdini. You know what SOP is, you know what simulation is, you know what volume is, you know what rendering is, and you are comfortable with Houdini. We're not going to be able to go really basic here and explain everything from zero. We're going to do a little bit of introduction, but then quickly ramp up and get started into the more advanced things. Thank you so much for watching, and good luck with everything. Bye-bye. Hello everyone, and welcome back. This video is for everyone who took the first workshop that we did called Mastering Pyro Effects in Houdini. And this was a 10 weeks workshop that covers pretty much everything there is about Houdini, but it was done 3 years ago and it only covers mantra. Since then, we have been trying to create Mastering Pyro Level 2, which we've done a lot of R&D for, but at the same time, Side Effects was changing everything under the hood. And by the time we finished R&D for Mastering Pyro Effects Level 2, which included an airplane going through smoke and a lot of custom things, by the time we finished the R&D for that workshop, which was like 5 months of work, Side Effects released a new Sparse Solver. But the thing is, they didn't talk about is that the Sparse Solver comes with a new combustion model, which is the majority of the custom or the work that we did in this workshop was how we can create our own combustion model. And the main reason we did this is because we want to do something more advanced with Houdini. We want to customize everything. But then the new solver, the new Pyro Solver that came, or the Sparse Solver, it's not clear that they have a combustion model, but they do, and it is actually much more stable. And they tried to recreate some of the Weta work that they did for the Avengers. So Side Effects worked with Weta team, and they tried to create a halfway workflow or something combined between what Weta did and what Side Effects wants to do. So we had to go back to the drawing board and say, okay, we're not going to do Mastering Effects Level 2 because everything has changed, and we first need to change the Mastering Effects Level 1, which is now called Explosion Effects in Houdini. And by doing this workshop, we realized that we don't have to do a Level 2 workshop. We're going to combine everything here and show everything we have, everything basically we want to share. We're going to combine it in this workshop, and not like the Mastering Pyro Effects where individual shots or individual sims were basically, you know, practical technical effects, like how to do this, how to do that. We wanted to use shot-based effects. So we're going to talk about the technical things, but we're also going to be reproducing production ready shots. The other thing that we did, because the solver is brand new, we had to do so many R&Ds, and I think I have like 450 wedges that we're going to share to explain how the new solver works, because everything is different. And then after all that R&D, I looked at it and said, okay, do I need to customize it? Do we need to change this combustion model? And we don't have to. Like the default is actually really, really good, not like the one in the Pyro Solver. So what I ended up doing is using the combustion model that comes with Side Effects, and then injecting extra things to it. If you're brand new and you don't know what I'm talking about, that's perfectly fine. Everything will be explained later. I just wanted to make sure that everybody who took the previous workshop understands that we're going to be going and learning new things completely. The basic is still the same. What a smoke field is the same. What a simulation is all of that is the same. Houdini has changed since 12. Okay, so we're not going to be talking about anything new there. The technical side of things is the same, but we're going to learn how to use this new solver and get the most out of it and see what we need to customize and how to use it, basically. Thank you for watching, and see you in the next video. Bye-bye. Hello, everyone, and welcome back. So I wanted to create these diagrams to explain the overall workflow of creating simulation in Houdini. And I wanted to explain it in a way that will make it easier for us to teach later, and everybody understands where the steps and what needs to be done to make this workflow as efficient as possible. And as we go, we're going to be modifying or creating our own tools to fill in each of these steps. Okay, so what do we have in general? We have a source, which can be made of points, lines, or geometry. We take that source and create a volume from it. This would be a density field, this would be a temperature field, or anything that we could pass into the solver. Then the solver takes all these inputs, takes all these volumes, and starts simming. You know, you give it data, it's going to run its calculation, and it's going to give you something back. So in this case, for example, we can take a sphere. Let's put some geometry here. sphere. So let's say we take a sphere, we convert that sphere into a volume, and then we pay a density volume and we pass it into the solver. Let's just call it volume. We pass it into the solver is gonna run the calculation needed and give us back a volume field. Now, as the simulation goes, it takes in, let's say, a density field, and it generates more than that. Because we have movements, we have temperature, we have a combustion model, it can generate temperature, flame, burn, velocity, divergence. All these things are internal to the solver, and when we want to render, we need to export and save the data that we need to disk. So in this case, we have a sphere going into the solver. We can inject extra force. For example, we can have a wind, we can have a character moving along and injecting velocity into the sim. We can have a collision geometry, we can have a wall, a car, a ground, anything. All that will be taken into consideration when running the solve, and then it gives us back volumes or volume fields. These volume fields, they are generally not compressed, they are raw data. Okay, because the solver needs to use the highest, well, it cannot use compression, because that will ruin the data and the math and numbers behind the sim. So the data is always raw. We export and stream out the data that we need and rerun it through an optimization workflow. Now, this optimization workflow is something generic. We can go into more details later, but for example, we could take the density field and compress it instead of 32 bits into 16 bits. We can take the density field, which generally fills the entire domain, and mask it to only be present where there is density. This will save a huge amount of disk space. We can take that. We can take the data and lower it. We can lower the resolution of a volume. We can generate points that we will use. We can fill the density with points and sample the temperature to give us a quick preview with points instead of having to display the viewport, for example, the volume. We can save it to disk. We save it to disk as VDB, and that's what we will render in Arnold, Redshift, and or Mentra. VDB is the format that we will use. It is a volume format developed by DreamWorks, and it's natively integrated in Houdini. Now, Houdini also has other types of volumes, or the Houdini native volumes, and that is what's being used in all the calculation inside of the solver. Okay, so everything happens with Houdini volumes, and then when we compress it or when we save it to disk, we convert it to VDBs and then save it to VDB. Okay, so this is the general workflow. Now, what we can do is, because we have these steps, we can work on each one of them and make it and customize it the way we wanted it to be. Let's say we want to emit explosion. Okay, we can create our own spike system, our own emission system. Okay, you select a point, and then it creates lines, and then you randomize those lines, and you create like cones, and you place it on top of these splines and convert those cones into volume. You then create velocity, and that will be your source. Okay, same thing for the solver. We can dive deep and customize it. Same thing for the fields. We can import specific ones that we need. We can delete the ones we don't. We don't have to. We can customize each of these steps. We can customize the collision geometry. We can customize forces, the optimization workflow, except the safe. So each of these things, we can go and dive into it and make it as custom as we wanted it to be, to give us the control that we want. And as we practice, we're gonna see a connection between all these steps, like what the source and how does it look like, how is it moving, how big it is, and how fast it is, and how many points, and what kind of fields, and how all of that goes into the solver. So all these things are chained and connected together, and we're gonna learn how to customize and create all of these steps. Now, what side effects did is, with the latest Houdini 18.5, which I don't recommend using at any point before maybe week 6. Okay, we don't want to use any of the new stuff, because it's just gonna skip, and it's gonna basically, it's gonna skip a lot of the important things that we want to teach you. So what side effects did is they looked at a variety of workflows and how people are doing things, including our workflows, and they've designed a system that tries to compensate all of the workflows and gives those control, which is great. It's amazing. So, but we don't want just to use that. We want to be able to create that, customize it, change it, and fully understand how it's working and why it's behaving like that. The other important thing as well is Houdini SOPs is a crucial part of learning Houdini. The more you know about SOPs, the better artist you are. And by simply using pre-built solutions from side effects or any other artist, we are not giving you guys the important information that we need. Everyone has to know Houdini inside out to get to the senior level, or the level that very few has, and that's the one that will make you stand out. If something becomes accessible and it's easy, everybody can do, then the market will quickly get crowded and it will be really hard to stand out from the crowd because it is accessible to everybody. So we don't want that. We want to have the edge and be able to create something custom and control it and fully understand how to do it. So that's why we're gonna dive deep into all of this. In the next video, I'm gonna explain the new combustion model briefly, and then we're gonna continue and move on to some more stuff. Thank you guys for watching, and see you in the next video. Bye bye. Hello everyone, and welcome back. The next important part in the simulation process is the actual solver, and a crucial part of this is the combustion model, or how the sim is going to react to the data that we're going to give it. So for example, with the new Sparse Solver, which we are going to use throughout the entire workshop, has a new combustion model. And basically the way it works is we have two inputs, a density and a flame. Okay, we can call it anything. We can call the name whatever we want it to be, as long as we put it in a specific field called burn. And what will happen is this flame is going to go into the combustion model, and it takes into account the density, and it's going to generate divergence and temperature. Temperature is how hot the smoke is. It's not the same thing as the flame. Okay, you can have a fire, but then it's a small amount of fire, but then the heat or the temperature around that fire is much higher, and it spreads and it diffuses very, very quickly. So the temperature area is not the same as the flame. And the way the smoke expands or grow is by respecting the divergence field. So the combustion model is going to generate divergence, and it's going to change the temperature field. The divergence will cause the smoke to expand. Okay, the temperature and the buoyancy is what will make the smoke rise. So hot smoke will go up, and it will also expand, and all of this will go into the smoke sim and get affected and repeated again. Okay, so we plug in two inputs. There's a combustion model that will generate other fields, and then all of this data goes inside the smoke. We can also inject anything else we want from external sources, like a velocity field or a pump force or anything. And again, if you're new to all of this, everything is going to be explained in depth once we start building things in Houdini. So this is the new combustion model. I like the way it behaves. I like the way it moves, and I don't think we have to customize it like we did in the mastering pyro effects in the old approach. I think the new one that Side Effects has is very, very solid, and I think we can get a lot of things done with it. It does not mean though that we're not going to customize it. We're going to be injecting things to it. We're going to be slightly changing and modifying it, but it's not as extreme as we did before. In the previous workshop, the combustion model was not great, and we had to build our own to satisfy the need for what we wanted to achieve, but we don't have to go through that again. Cool guys, thank you so much, and see you in the next video. Bye bye. Hey guys, and welcome back. So let's take a look. We have Houdini, let's create the DOP network, and let's hit tab and type in smoke. So we have smoke configure object, smoke object sparse, smoke solver sparse. I'm gonna create a smoke solver, and I'm gonna hit tab and type in pyro. And you can see we have a pyro solver and a pyro solver sparse. Sorry, a pyro solver sparse is what I need. Sorry, a pyro solver is what I need. So the pyro solver is build on top of the smoke solver. So what we have is the default or the simulator node, the simulation process, plus a combustion model, plus old combustion, I'm gonna call it like that. And that gives us the pyro solver. Now this is the old workflow, okay? The new workflow, I'm gonna create smoke, type in smoke again. You can see we have a smoke solver sparse. And then it plus, if we add a combustion, the new combustion model to it, that gives us the pyro solver sparse, okay? And you can see the UIs are very different. And this one, this is the smoke solver. And you can see it's much cleaner, very, very clean. And then we have the pyro solver, which is pretty much the same except these two tabs. So it has built-in a built-in combustion model, and then noise, which is similar to what we had before. And this is what we're going to be using. Now, this sparse feature is a bit confusing because what it means is there's two things to it. Okay, if I go to the tab, there's two things. There's the sparsity. Actually, no, this one. Yeah, so there's the sparsity and the resizing. Okay, so it has an adaptiveness and a sparse. What that means is it's gonna auto expand the bounding box to always fit the data where it needs to be, but it also adaptively change the resolution of the voxels, which we'll explain. I don't want to dive so deep into this, but there's two sides of this. There is the sparsity of it, and there is the resizing feature. There's two distinct things. If I want to use this thing, the pyro sparse solver, I can use it without the sparse feature by simply turning this off. Okay, now I have a solver, and it has a new combustion model, and it does not have any sparse feature. And that is something we may want to do, because the sparse is basically adaptively changing the resolution of the data back and forth, and it may not necessarily give us the result that we need. So in this case, I wouldn't call this sparse, it's just a new cool pyro solver. Okay, it has a combustion model, it has an auto resize feature, and that's it. Okay, and this is what we're going to be using. We're going to be turning on sparsity when we need it and if it makes sense. It does not make sense to use it in all cases, and we're going to look in depth into that. And this is the new workflow, the smoke solver and the new pyro solver. Now the smoke solver is also different from this one. It has the sparsity feature, it has the auto resize feature, and it has a much more simplified controls, and it has a newer temperature or a newer buoyancy model. And what this means is, before, if you put temperature, the smoke always goes up. But now what they wanted to achieve, or what I was trying to achieve, is when the smoke also cools down, it can start going downward. Instead of going up or lingering at the same space, you can have it go down. And this is very practical in case where you have sand, for example. So you have sand in the explosion, you emit all of that, and then eventually the sand will start falling down. So this is what the ambient and reference are for. You have a minimum temperature, or like a normal temperature. You can go above it, but you can also go below it. This is not something you could do before. I personally was not able to get the sand to fall from the explosion. It's not as simple as it seems, and I think we need to do some extra work to get it to work, to get it to give us that behavior. But we're gonna use it. It's actually really simple, and we're gonna treat it similar to how we wanted it to be. And then if we need that specific look or that any specific feature that we want, we're gonna build that in and customize it. So this is the stuff. This is the new stuff. This is what we're gonna be looking into and diving into. Thank you so much for watching, and see you in the next video. Bye bye. Hello everyone, and welcome back. Part of the workflow and the work we do is to test rigorously everything Houdini has to offer, especially when something new is released. And at Rebelway, we do this thoroughly whenever we have something new and we need to learn how to use it. Igor Zanik does a lot of the work when it comes to Houdini Flip Fluid and wedging and testing all of this. And we use similar workflow for Pyro and or any other solver that we want to test. What we've done is we've gone through every setting, every option this has to offer, and we tested it. We tested it at different parameters. We tested it under different conditions. This workflow is very, very solid and will allow you to quickly test things out. And it's very, very simple to use. You can go as fancy as you want with building something similar in TOPS or using command lines or using Python. It does not matter how complex the system is or what technique it uses. The end goal is that you are able to test and wedge things and compare results and see them in the viewport. So we have this new system, right? We have a new temperature model, we have new advection methods, we have all these controls, and we want to learn how to use it. So what we've done is we've created a small library or a large library testing every single parameter there is in the solver. Okay, and I'm going to show some of the final results. So for example, we have this is for the combustion model. I'm going to skip that. So let's say, for example, we want to test the disturbance. Okay, we want to test the disturbance under the shape, this one. Okay, we want to see how it works. It has a variety of options and we want to see how it works. So we've created files and we've created hip files, and each one of them has a different setting. And you can see here, this is the setting or the value that's been changing between these 4 variations. And the idea is to do one test at a time and then combine 4 side by side. And this will easily show you what that value is doing to the sim. Okay, and you have access to the hip file if you want to go back to. And by doing so, we can easily wedge out the turbulence settings. We understand what the scale does. We can test the combustion model. We can test everything we want. So this is a quick one to show how the system works. And you can put any setting you want here. Okay, you can test any value, and we've done. And you can add anything else you want. So for example, once we get to a more advanced setting and we want to try and create, let's see, we want to try and create, for example, we have a sim that we like, okay? And I want to try some complex cross product or some complex techniques on how it would affect the sim, on how the sim would look like. I can start creating all of that. Okay, so for example, here I have a basic sim and I'm testing a technique to add cross product force based on the sim to give it that extra rolling effect. And I can add notes here and explain what I'm trying to do in the sim, and then move on to the next one and then add some more features to it. Unfortunately, I've started, because I was running out of time, I started using the full name to express what I'm trying to do. But all of these workflows can be used to test simple settings as well as advanced techniques. Okay, so and we're going to provide the hip file for all of this. So let's take a look, for example, at the turbulence. Okay, so this is all the settings, and I'm going to put it here, always on top. And let's take a look at the turbulence setting. And this is the values. So you can see the file name is, this is the base. Okay, this is the default setting that would come with the solver. This is the base. And then I wanted to explore what the gain does. Okay, so I set it to 1, and then I set it to 0.5, and then the influence, I would reset the gain back to the default value, and then the influence, this value, the influence threshold, I want to see what that does. And then the scale, which would be somewhere, the swirl size, or no, the actual scale, I think this one. I want to see how that affects, and because it is a very important control, I can test a variety of values, 3.6, 9, 0.15, 21. I can test a variety of values and take it all the way from 0 all the way to extreme. And then the swirl size from 1 to 100, and then the turbulence frequency, I believe it would be the levels. Yeah, so 1, 2, 3. And all of this is, each test is here. And I tried to do 4 for each control so that it can put them in the same graph. If I do more, I would pick the ones that would make sense to be viewed together. So these individual tests are from each file, and then I run another process that groups, and I handpick the files that I want to put them side by side, and we have a separate file for this. So for example, the gain, I now have this file that shows me gain 0.5, gain 1, gain 0.5 here, and gain 1. Again, because I didn't have a lot of values, I just put the same file. I'm not sure, maybe it's different. Yeah, I think it's the same, just putting it side by side. So that would be one test, and then the influence. So the influence value is changing here, and you can see how that affects the sim. Okay, and then the scale. Obviously, this is not something, the 2, 1 at the bottom, we don't want to go there, but you can see a value between 0.6 and maybe 0.1 would work. And then the swirl size, this is actually very, very cool. So for example, you can see how awesome the swirl size here, and then the sim. So what's happening on these flickering boxes is the sim on a specific machine is running out of GPU memory. Okay, so it's not able to display all the data, but all the other workstations are able to do so. And we have a small farm, and not everything is ready for GPU rendering, because this will require maybe 2 to 4 gigabytes of memory, and I don't think that workstation had. It had like a graphic card from 8 years old or something. So, and this is the turbulence variation. So let me check. Yeah, VLC is trying to put the list all together. So the turbulence 1, 12, and then 12 and 1. Yeah, when I only pick 2, I just duplicate the same result, and I can see them side by side like that. Cool. So this is the approach, and I have everything pretty much. So I have the turbulence, I have the disturbance, I have the shred option, and then the anticipation is very obvious what it does, so I didn't test that. But then we have the combustion model. So this is also, we've done all kinds of testing to the combustion model, and we're going to take a look at them in depth later and study and see how that affects. And by looking at this, for example, I can have a starting file, and I can just browse, say I like the turbulence of size 0.5, for example. I like the shred of 0.1. I like the disturbance of 0.2. The combustion model, I like these values. I like this temperature, this buoyancy. I can use that as the base, and that's what we've done. So because we have this library, we can then start to use it as a base. Okay, so we start with the gathering base, which I pick the settings I wanted, and that would be my base. I do a test, and then I start adding custom forces on top of that to do my own research. So all of this is built on a test where I liked all the settings, and then everything else is basically me trying all kinds of techniques and all kinds of tests to basically try all ideas I want. Okay, I have an idea about combustion, I have an idea about custom forces, I have an idea how to tweak the flame, I have an idea of anything I want. I do a HIP file, I do a test and see how it looks, and I decide from there. And the goal from all of this is to give the student a deeper understanding of all these options and a base of what to use. So instead of starting lost, you don't know what this does and what that does, by simply going through these files, you will fully understand how everything works. And this system can easily be injected into other files. So if you have a different setup and you want to use that, you can definitely use it and put these nodes in, and you should be able to have the same graph and same preview. So we're gonna continue studying this in the next couple of videos. Thank you guys for watching, and see you in the next one. Bye bye. Hello everyone, and welcome back. We're going to be providing a couple of videos that are from a previous version of Houdini, and it's going to explain the basics of volume, what volumes are, and how to create a simple smoke solver inside of Houdini. These videos are this one, and it's gonna go in depth into that, and then after you finish watching them, we're gonna continue in the wedging workflow, and hopefully this process or these couple of videos are going to explain everything you need to know about the volumes and how the smoke solver works in depth. It's based on a previous version of Houdini, but all the principles are the same. So thank you for watching that, and see you in a bit. Bye bye. Hello guys, in this video I'm going to explain how volumes is stored and manipulated in Houdini. And I'm going to start by drawing a grid here with a set of points. And this is basically a grid with points. This is a normal geometry. And in Houdini, we can use a point VOP or a wrangle or anything to change the value of these guys. So what we can do is we can take these points, and using a point VOP, we can take the current position and apply a noise to them and move them in a different position. We can change the point position to be in a different location. We can also change any value alongside P. We can change color, we can add new attributes, we can create anything like that. And with points, the attributes are called attributes. Let's say P is an attribute, CD is for the color, we have velocity for V, and then N for normals, and we can create any attributes, and this is what they're called attributes. With volume, things are a little bit different. With volume, we always have a domain that we work with. So let's say this is our domain. Okay, and the volumetric data can only be represented in this domain. We cannot have data just randomly spread like we have with points. We can just throw points anywhere and they are not restricted by any domain. With volume, you always have to have a domain, which is basically a 3D grid. And inside this domain, we have what we call voxels. And what happens is each axis is divided into smaller chunks that constructs the voxels. So let's say we have 10 units here. It's going to be split every 1 unit, not this way, but basically it's going to be split in every axis, and then each one of these guys is called the voxel. Okay, the more divisions you have, the smaller the voxel is, and the more resolution you can store, the more precise your volume representation is going to be. Now let me try and draw another one. Okay, so let's say we have a sphere. We made a sphere out of volume. Okay, we see it here as density. Now, when we create data in here, there is actually voxels everywhere. This entire domain has voxels, but only voxels that are in this region, in this sphere, are filled with density. And these things, the density, for example, is in volumes is called field. It's basically attributes in the geometry. They're called these guys are called attributes. When we work on volumes, they are called field. So we have a density field, for example, and we have two types. We have a scalar, which is a float, a scalar field, and a vector field. And a vector field is basically 3 scalars. Let's say velocity, we have vel.x, val.z, val.y, and val.z. And with volumes, they are called fields. And in this case, the density field has a value of 1 in this region, and then everywhere else is 0. And in order to, we can manipulate any value we want inside this domain. So we can take this entire grid here and change the value of each of these voxels to something else. We can erase completely this sphere, for example, or we can add noise to it. We can change the current value and add noise to it. We can add new values here and make the entire domain filled with noise. We can generate a noise and multiply it with this sphere, so we only have noise here. But the main difference with points, we can transform them in space without any problems. But for us to move this volume here 5 units this way, we cannot do that. We cannot move data in different in any position by treating it like points. We cannot do that. We have to do something different with volumes, and that something different is called volume sample. And what happens is, when we work with volume, when we run any operation, it's going to loop over each voxel, whether we use it or not, and then for that, it's going to sample its volume, its value, let's say the density value. It's going to sample that. And for us to move this data 5 units, we have to shift that sampling position 5 units, and then when it starts looping over, instead of this point here, for example, querying from its actual position, we can tell it to query 5 units away from its origin in this direction, and that will cause the entire sphere to shift this way. Okay, and we can do the same thing. We can shift the data in different directions using the volume sample. And let me create an example and show this in action. Okay, so I'm going to create a geometry node, and I'm going to create a box. And to convert any geometry into a volume, we can use an ISO offset node. And this will take the input geometry and convert it into a volume. Now we can increase the division here, which will generate more voxels, which will make the voxel size smaller and basically give us 100 voxels in each axis. And if we middle click now, you can see we have 100 by 100 by 100. That's the domain we have. Now this field, it's a float field, but it doesn't have a name, so we're going to give it a name. I'm going to call it density. Okay, now if I middle click, see, it's very similar to the point attributes. It's called density. And now to manipulate that, we're going to use a volume VOP. And this volume VOP is going to loop over each voxel, same as if we have points, and we can change that data. We can manipulate that data. Now see here, it has an output called density, and whatever we do here, we can import the density, manipulate it, and then send it back. So I'm going to create a multiply. I'm going to create a noise. And let's multiply this density by this noise. And let's plug it back. Now see, we're changing the density value. Okay, let me increase the multiplier. And this guy is returning values between -1 and 1. And I don't want the density to be negative because we can't view that in the viewport. So I'm clumping the values between 0 and 1. And we can also clump it between something, let's say, something like that, so we don't have empty data. And we can play with the noise. Okay, we can play with the noise. And currently, we're taking that field, changing its current value, the value of each voxel, and then exporting it back again. Now, let's say we don't have a box. Let's say we have a teapot. Let's create a teapot. Okay, and let's run the volume VOP. Now look at how the noise is only appearing where there is data. Okay, and that's because we only have density here, and we're generating noise and then multiplying it. It's not changing these values. Now, if let's say we want to move these points, we want to move the teapot from this, from its current position to a different location. We cannot do that with this. We cannot do that by manipulating the volume, the density itself. We need to offset the sampling position at, and instead of having the current sampling go over each voxel, we're gonna offset the position where each voxel sample its data from. So instead of having this point here sample from that location, we're gonna tell it to sample 5 units away. And then this point here, instead of it's gonna sample from this location, it's gonna sample from 5 units away. And that will make this density show up here. Now let me add a volume sample. And we're gonna pass in the sample position, which is P, and let's plug it back in. Okay, and for the input, we're gonna set first input, and it's gonna pick the first primitive, and the reason for that is because if we look here, this is number 0. It's the first one. We can also change this and tell it to only import the primitive number named density. Okay, now we're getting exactly the same result as if we have this. Okay, exactly the same thing. But what we can do now is we can change the position. Now let me add something to the x to the x-axis. Let me split the vector into x, y, and z. Okay, and then let's add value to the x, and let's create the vector again. So float to vector. And let's use that instead of the sampling position. Let's use this new one. And now we have this input. Let's expose that and go up. And let's move the slider. And now it's moving. The data is moving. Let me show the original geometry. Let's go back. Sorry, I've connected the wrong input. Yep, so see now we're moving the teapot in space. We can also, we can modify any axis we want. We can change the position of any of the axes. You can see now we're shifting the data, okay? We're changing where each of this voxel is sampling its position from. And we're adding this offset here. And what we can do is, if you guys remember when I did the noise here, the noise is not breaking these edges, and the reason for that is because we're not telling any voxel to sample from different location. Each voxel is taking its value from its current voxel position, and we're just multiplying the values by a different amount. And if we want to break the edges, we can simply take the position itself and add noise to it. So here, let me create a vector. I'm gonna set it to 3D noise, and let's reduce the amount. And now look at this. We're disturbing the sampling position using this noise. Okay? And that's how you manipulate data in volumes. Now, there is two things you have to remember. If you want to change a value of a current voxel with something new, you can bind import any field and then bind exported using, for example, like the density. If you want to have a voxel disturbed or the position sampled from a different location or transform this, you have to use a volume sample node, and that will tell each voxel to look up its data from a different location. So these are the two main difference. And then these guys are called are called fields, and you can give them any name. And generally we're going to be working with density, temperature, and velocity. Those are the three things that we're going to be creating. And now to the next thing, which is the volume types. And if you middle click here, you can see there's this type is called volumes. And with Houdini, there's another type of volumes that has been recently introduced, and that's called VDB volumes. So a VDB volume is much more efficient, memory efficient. It has a lot of new features, and it has an actual vector type for fields. There's fields that are vector type, and with Houdini volume, everything is just scalar, and for volumes, it just uses a 3 scalar, and with VDB, this is much more efficient. So to convert any geometry into a VDB volume, we use a VDB from polygon node, and you can just plug that in into the node. And by default, it's going to try and create an SDF. We're not going to be using SDFs, this distance VDB. We just need a density. And then this is the voxel size, so I'm going to lower that. And you can see we have pretty much the same result here. Now let me convert this into an actual mesh instead of. Okay, and that should, yeah, it's not generating the shape there, but I'm not going to worry about that for now. So you can see we have some data, and we can use the same volume BOP with this data. It's exactly the same. And the main difference, if you middle click here, you can see it's called VDB, and then if you hit tab, there's all these options, features that we can, nodes that we can use to manipulate this data and do a lot of cool stuff that hopefully we're going to be exploring. So this is the main feature, the main core of volume manipulation in Houdini in SOPs, and we're going to be using that to create the fields, a variety of inputs for the DOP sims that we're going to be creating. Thank you guys for watching, and see you in the next video. Hello guys, in this video I wanted to explain the DOP context and how Smoke Solver works by default in Houdini. And currently, if you're familiar with SOPs in Houdini, you know that you have this context that you have, you can manipulate points in it, and you can also manipulate volumes, voxels, and things like that. But when you want to create sims, you have to use the DOP context. And basically, the DOPS is a different context where the data is represented differently. So what happens is you have data coming from SOPs, let's say points. If you're using particles, you have voxels, and you have forces, any other volumes as well. And all of that from SOPs goes into DOPS, okay? And then DOPS creates its own representation of the data, where it has an object, which is basically a placeholder for the data, and then the data gets attached to it. Let's say you have, you're going to create a smoke sim. There is an empty object that gets initialized, and then that empty object will have data attached to it. Let's say we import the density field, for example, in there. And once the data is initialized, it goes through a solver that's gonna integrate the data. So this solver can take any data, any input, and integrate it over time by applying multi-solvers. So you have a multi-solver node that basically takes this input and applies any micro-solver attached to it. And what a micro-solver is, it basically takes the data. If it's a volume, you have a set of micro-solvers that you can use. If you have points, you have specific ones that you can use. The microsolver will take that data and process it, do something to it. For example, we can import the density field and run a gas blur to it, and it will keep doing this over and over and over. And so in this example, I'm going to show how to import data in DOPS from SOPs as a smoke object, and then how to attach it to the smoke solver, the default smoke solver. So we're gonna import the data, and then we're going to pass it into the smoke solver, and then once we initialize the data, we're going to source something into it, and it's basically adding data. At first you attach an empty placeholder and then you fill it with data. So you have the incoming, which initializes the placeholders, and then that goes into the solver, and the solver injects the data onto them and runs the micro solver. So let's take a look at a simple smoke sim. I'm going to create a null here. I'm going to call this out density. I'm going to create a DOP network. Okay, I'm going to dive inside. Don't need that. The first thing we need for a smoke sim to work, we need a smoke object. Okay, and this is what basically initializes the data. And let's see, we need to give the domain, this object, enough space to import the data, because this is what will define where the sim is going to happen. Okay, so something like that. We can also control the resolution of the sim. And then we're going to create a smoke solver. And this is one of the Houdini native solvers. And you can see here, this is where you attach the data, and this initializes the solver. And if I hit play now, nothing happens because we're not importing, we're not sourcing anything. And to source data from SOPs, we're going to use a source volume node. So I'm going to create that. And then here we're going to tell it to source smoke, that's what I want, and point to the out density. And now we should see the data imported. And you can see it's already emitting the density over and over and over. And let's hit play. We should see it incrementing. Now the resolution is really low. Let me increase this a little bit. And let me put down a gravity node. And let's take a look. We should see the sim falling. Let me increase the size of the domain so we can see it. Okay, let's hit play. You can see the smoke is going. So great. This is how a basic smoke sim works. Now inside this guy is where the solver is doing the computation to make this density field behave like a smoke. And if we double click, you can see it's basically built off a lot of nodes. There is this gas substep node here, and then there is a multi-solver that takes the data, and then it runs all these micro solvers based on various switches, and then sources the data which we have here. So it initializes the data and then run one step and then sources this guy and keep doing that over and over. And in the next video, we're going to create a smoke solver from scratch to understand what's happening inside the smoke solver in the first place, and what are all these micro solvers and how they're working, what their purpose is. And hopefully with this explanation, we'll have a much better and deeper understanding of how Houdini smoke solver or solvers in general works. So we'll do that in the next video. Thank you guys for watching, and see you in a... Hello guys, and welcome again. In this video, I wanted to talk about a little bit of theory behind the smoke sim itself, and then we're going to apply that here and create our basic smoke solver. And I'm gonna draw 2 voxels here, or actually let's draw more. I have, let's say, 6 voxels, and I have density of 1 here, and all these guys, they have 0, 0, 0. Okay, and then we have density of value 1, and what's going to happen, we're going to apply velocity to it. We're going to advect this data. And what advection means is it takes in an existing data in space and then moves it, basically offsets it by a specific vector. So let's say you have points, you add transformation to them. So that's what advection is. It just takes an existing data and moves it through space. And this guy here, we're going to advect it to this cell. So the next frame, it's going to have the data in between. Or let's say it's going to move the data here all the way here. And by doing that, this voxel is going to need a certain value. Now where it's going to get its value from? It's going to get its value from the neighboring voxels. So let's say we have another one here of 0.5. Okay. So once we move this guy into this voxel here needs to readjust to get its value to fix basically what happens. So if we move this data, it's going to suck in from the other voxels. So it's going to import, it's going to suck in this data here and then this guy. So we'll get 0.5 and 0, which will be merged together into this cell. And then we'll keep doing that over and over. So the next frame is we're going to keep advecting this guy over here. But in this frame, the velocity is not as strong as this frame that it moved the data completely by one voxel. It only moved it by half a voxel. So we have 50% left here and 50% on this new one. And then in the next frame, it's going to take 50% from here and moves it here. Okay, we're going to have 0.25 and 0.25. But after doing this, after a few steps, the density is going to smudge. It's going to blur. And this is one of the main problems of smoke solvers in general, is data loss. And in order to make this physically correct, the smoke solver, when it moves data, it needs to correct its pressure. It needs to keep the pressure the same. And the thing that maintains the pressure is called project non-divergent. And the divergence needs to be always equal to 1 in a cell. And when this data moves in, it lost all its values. So it was 1 here, it lost all its value. So this guy is going to try and compensate for that. So it's going to import data from here and data from here. And then this guy is going to also say, oh, my data has changed. I need to get more values. I need to check my other neighbors and get data from them. And we end up touching all the voxels, moving all the data of all the voxels by just changing one of them. And the project non-divergent is what solves this equation to move the data throughout all the voxels and give them the value that they need to keep their pressure realistic and physically correct. And this is what happens basically in a solver. You have the data, it comes in, it initializes the voxels with certain density value, you apply velocity, a first advection happens, and then that density moves. The project non-divergent kicks in to compensate and correct all the other voxels and give them the correct value, and then it keeps doing that over and over. And we're going to do these steps. We're going to import the data from DOPs, and we're going to apply an advection using certain velocity, and we're also going to fix the diversions to give each voxel the correct value that it needs. So what I'm going to do here is I'm going to use this density, okay, and we need some velocity. So what I'm going to do is, let's see here, I'm going to copy this, and actually let's do this. I'm going to change the name of this density, and I'll explain why in a second. So basically in Houdini volume, a vector is 3 scalars. One is called that are matched by name. So if we create 3 scalars, one called val.x, one called val.y, and val.z, we'll create a vector, a velocity vector. So I'm going to take this guy and use a name node to change the name of the density. So here it's called density, and I'm going to change it from density to val.x, and then here val.y, and then here val.z. And these are 3 unique volumes now. All I have to do is merge them together to get the vector field that I need. Okay, and now I have a velocity field. I'm going to hide those. I don't need to see them. I'm going to use a visibility node and say hide everything, and now they're hidden. Okay, now what I'm going to do is let me add these guys. Let me merge them together. Merge the velocity with the density, and I'll explain why in a second. Or actually, I don't have to do that. Now what I want to do is I'm going to modify this this volume here. So I'm going to create a volume VOP. And to access any field, this vector field, we're going to use a bind import. So bind node, it's a vel, the name is vel, and then a vector of type vector. I'm going to generate a noise using P, and actually I don't need this, or yeah, I don't need that. We just need to bind export this, because we're not going to modify the existing data. We're going to just create our new one, and let's set this to 3 vectors, and let's increase its value to 10. I'm going to export this as well, and it's a float, a vector float. Okay, now what I'm going to do is I'm going to scatter some points on this volume, and I'm going to use those to preview the velocity. And there is a very useful node called volume trail, and with this guy I'm going to connect the points and then tell it what volume to display, and you can see this is what the velocity field looks like. And we can use another node called volume slice as well. You can plug it here, and you can see it's displaying the voxels, the velocity field as a mesh with colors, and this is what the velocity looks like, and this is the direction. Cool. So I'm gonna copy this and call it out velocity, and let's create a new DOP. Okay, and I'm gonna dive inside, and now we're going to create the solver from scratch. So I'm not going to use any smoke object or any smoke solver. I'm going to create an empty object. Okay, and then what we need is we need to import the data from DOPs. So for that we're going to import a scalar field from SOPs. So the node for that is called SOP scalar field. Okay, and I'm going to use a tick on use SOP dimension, and then browse to the path. So it's called out density. And right now we're not seeing anything. The reason for that is because there is no way to tell DOPs how to visualize this, and to tell it that answer, to give it that answer, we need to use a scalar field visualization node. And the way the data is connected is a little bit weird, but basically this is where you attach data, and this is the visualizer that you can attached to view this data. So I'm going to take on show guide geometry and use smoke, and now I have the data viewed. And the next thing we want is we need to import the vector field, and for that we're going to use a SOP vector field, and I'm going to use SOP dimension and same out velocity. And to visualize this data as well, we need a visualization, a vector field visualization, and we can use different type. Show guide geometry. You can see now we're displaying it as as streams, and we can say by speed, and we can see how the velocity looks like. Cool. Now if I middle click here, you can see it's called vector field and scalar field. I don't need those names. I actually need them to be called density and vel. So the first one is density, and the second one is vel. Cool. Now let's create a multi-solver, which basically takes any data and applies any microsolver, and whatever is relevant between the data and the microsolver will get integrated, and we'll see a result. So let's say if we go here, I know this is a little bit overwhelming, but trust me, we're going to be able to fully understand this. I'm going to use let's say a gas blur, and the name is clear what this does. I'm going to connect this in here. I'm going to tell it to blur the field that is called density, and the radius of the blur is, let's say, 4. Okay, that's it. I'm not gonna do anything else. Let me turn this off. I don't need it. I'm gonna hit play. Boom. The data is blurred over time. It's not blurred all at once. Let me reduce this to 0.2 and hit play again. You can see it's incrementing. It's repeating that solver over and over and over. Okay, let's try a gas dissipate node. And this basically takes any field and dissipates it over time. So we want to dissipate the density, and let's evaporate, evaporation by rate. I want to subtract, this is a percentage, so it's gonna subtract, let's say, 10% of whatever density I have now, or whatever value of this field, I'm gonna subtract 10%. And when I hit play, it's gonna keep doing that over and over until the data basically finishes. Let's say 0.1 doesn't seem to be doing anything. Yeah, so 0.5 is more visible, and now the data is dissipating over time. And this is a sim. This is an actual smoke. This is an actual volume sim. It's not a smoke sim because we don't have any smoke behavior, but it is a sim. So the next thing I'm gonna do is we talked about advecting these fields. Okay, so let's take this velocity, this density here, and move it by applying that velocity field that we did. And the node for that is actually is called gas advect field, as the name suggests. And it takes a velocity field and the density that you want to advect. Okay, and if I hit play, you can see it moved that data using this field, using the velocity field that we imported. And actually the name doesn't have to be anything. I can call this temp, and then I tell it to advect temp, to advect density using the temp, and see we get the same result. It's just a field. And let's rename it back. But what's happening now is that every time it advects, it's actually the volume. There is a lot of volume loss happening. So the voxels are not keeping their values. They're just moving over time. And what happens is everything else needs to adjust when this happens. And to solve this equation, we need to use the gas project non-divergent. And there is 3 different versions of it. There's the gas project non-divergent, and this is the most complete node. And then there is 2 other ones, project non-divergent, that are used in various different places. And this is, I think this is the original one. I can't remember. Yeah, let's try this. They will all work. So I'm gonna advect the density and then correct whatever happened to all that data. It's going to be corrected. So the velocity field is vel, and then the goal divergence field is divergent. This is the data that this node needs. And so when we hit play now, we're seeing something a bit more realistic. Now the boundaries of this is limited, so I want to expand that. And the way I'm going to do that is using what's the node? I don't know the node in DOPS. So I'm going to convert this, I think, let me see, volume. Yeah, let's try this. Nope. Yeah, I can't remember the node. I honestly never use the Houdini native volume that much. So I'm going to convert this into a VDB volume, which should give us exactly the same result. And here I'm going to set it to VDB. So this type is VDB, which should give us exactly the same result. And then I'm going to use a VDB activate node to expand the boundary. You can see now we have more room for the sim to work. Now it's going to be slower because we have more voxels to work with. We've made the grid a lot bigger, and so that project non-divergent is going to have to worry about more voxels to solve the equations for. So when we hit play now, you can see we're getting a more realistic result. The data is not being just smudged. There is more interesting movements happening. Okay, so the next thing is I'm going to do one more thing. After we advect the density as well, we need to advect something else, because if you look here, the velocity is, we will fix the edges. The velocity itself is not changing, but it should. It's also being affected by this, whatever happens in the voxels. So for that, we also need to advect the velocity. So gas advect field, and we're going to advect the velocity by itself. And for this to work properly, we need to tick on allow self advection, and this will cause this node to create a temp field that it moves the velocity into, and then it advects it. And now we should see a more realistic sim happening. And I'm not sure why it's dissipating. I think there is some volume loss happening, but you can see it's the data is working correctly. And let's try with this guy, the multi-grid. Yeah, this is the one I used to use. Let's see. Yeah, I'm not so sure why it's dissipating. I think I turned off the I turned off the gas dissipate, but it's still dissipating. I'm not so sure. Now, one thing that that streak effect is called because of the extrapolation type, because of the Porter type. I'm going to set it to constant. And the voxel sampling for the velocity field, I don't want it to be at the center, I want it to be at faces. And this will give us a more accurate sampling. Now let me set this to constant, and that should be fine. Now let's try this. Yeah, I think, yeah, that was it. I think this is a much more accurate sim now. Now, the last thing I want to do is I want to also expand the velocity, because right now we're just expanding the density field, but this guy is still using the old domain, so it's much smaller, and I want to expand that as well. So I'm gonna move this, and I'm actually going to copy these two nodes and paste them here. So now we have the 3 vectors, and we should have our velocity working as well. Cool. Everything seems to be fine. Let's go back and hit play. Yeah, it's a little bit slower. I'm not so sure why is that. Let me check the resolution. Yeah, the volume is fast. Okay, let's try one more time. Yeah, I'm not so sure why it's slow. Hello guys and welcome back. In this video I wanted to show the sim and explain how to import the data and how to visualize it properly in Houdini. So it looks like I got the object cropped for some reason. I don't remember why this has happened, but basically it's still working, and you can see the sim is going upward and we have all kinds of interesting behaviors happening. Now let me play blast this to 80, let's say. I just want to show see this in real time, and this is actually a very high it's a mid-res sim, and it took just a couple minutes for it to finish, and we can debug this and get to the bottom of what's causing the slowness and where the most of the time is spent. If we wanted to, we can easily find out where the time is being spent and what's causing it to take this much time, and this will allow us to fully understand why the sims will take X amount of time to sim and finish, and be able to debug them easily later. So this is the final sim, and you can see it's fully functioning. It's a proper fluid sim, and this is actually could end up being a very interesting effect if we wanted to work on it. And what I wanted to show now is how to import the data in DOPs. Why is this here? Shouldn't be here. Yeah, it's gonna, unfortunately, the cache is gone. So let's see. To import the data in DOPs, we use a DOP import field. Sorry, to import them back in SOPs. Let's see if I can draw this. So we let me delete this. We created a sphere, the density, in SOPs. This is density, and we imported that in DOPs. Okay, and then we run the sim, and then we have a new data inside. So we're going to import that back in SOPs to visualize it from DOPs. Okay, and we need to access it. So to do that, we're going to use a DOP import fields, and we need to paste in the full path here, and then the full path / the object name. And now all we have to do is set this to smoke, and that will create all these fields ready for us. We don't care about importing velocity from DOPs, and we don't care about importing rest because we don't have that. And now we have this frame, and we also have a temperature field. We don't. We have another field called temp. Okay, it's not a temperature field. It's called temp. That's what we used for the buoyancy mask to make this go up. And to visualize this, we need some lights to get some shadows and stuff. So I'm going to create a light, and I'm going to set it to directional. Okay, and I'm going to hide this. I'm going to copy it and rotate it the other direction and give this a blue tint, and this a warm color, and let's reduce this to 0.4. And let's take a look. Should see some lighting on the smoke. Yeah, there it is. And I'm gonna change. I'm gonna dive inside and use a node called visualization, and this allows me to alter the volume density just for OpenGL preview. I'm not gonna change the value. I'm just gonna change it here to have a stronger density. You can see now we can see more visibly the smoke. The only reason we didn't see it here is because the density is really low, but it doesn't mean it's not being simmed internally. There is the values and everything. And I'm going to increase this to 2 to catch more shadows. And you can see we have all kinds of crazy details. This is actually a mid to high res sim. This is, sorry, a low to a mid-res sim. We're getting to the high level, but you can see we're getting so much details with just these 3 nodes, and we haven't done anything yet. We haven't started digging into this yet. So you can see we can squeeze out a lot of details, and this was very fast to sim. And the other thing I wanted to show, which is part of the custom stuff that we're going to be doing, but I'm going to show you guys this now. I can read that temperature field, which not the temperature, the temp. It's just a name that I used. And I'm going to set this to 1. And we're going to be able to see this. Now let's see. Yeah, it's starting to show up. Let's try 1000. Yeah, there it is. That's our temperature field, the temp field used as a buoyancy to move the volume up. Now I'm going to use this option here to grade it to look like fire. And I'm going to just set the preset to black body. I'm going to tweak the colors a little bit more. Okay, and let's work on the ranges to get a better visualization. Now the other thing I'm going to do is I'm gonna sim a couple of frames, because that frame that we have doesn't have a lot of interesting shapes. So I'm gonna do this real time so you guys can see it simming as well in real time. And we'll wait for 15 frames. And right now it's caching the data to memory, and depends on how much memory you have. You may have to, you may fill out your memory by this real-time cache, and depends again how much memory you can extend this to be able to cache more frames or less. You can also tell it to automatically switch to use disk caching if you want to, and I'm going to show where that option is. This go up. Okay, let's stop here. And the option to control the cache size is under the cache, by default set to 5. I'm setting it to 20, and you can take on allow caching to disk, which is off at the moment. So this is the sim. Okay, and we have this much voxels. I'm going to visualize it using this node, and you can see now we can display that temp field using this guy, using this field that we've created, and remap it to use this color visualization. You can see we're getting some kind of fire inside this sim. And again, this is all from scratch, and this is how you import the fields. For now, we don't have any velocity or rest, and we're not going to be using them. To cache this properly to disk, I would create a ROP output and save this under sim v1 sim.v1 frame geo.sc, and then you set the frame range, and it will cache the data here. Just hit render, submit, save to disk, and make sure to untick the cache simulation. There's also another option inside the DOP here, inside this empty object, called caching. It's best to link both caching of the upper level and this level together, so that we have they're both synced, and this feature can use extra memory if it's left on and this guy is off. So make sure you do that, and you hit save to disk, and then everything will be saved and ready to use. Thank you guys for watching, and see you in the next video. Hello guys, and welcome back. In this video I'm gonna try and explain how the solver steps work and what's happening under the hood. So let's say we have voxels with 0 all around, and then we have one voxel that has a density value of 1. So only this guy is filled, and then everything else does not have any value. Everything else is 0. Or maybe this guy has a 0.5, and then this guy has 1, and everything else is 0 around it. And we're going to apply some velocity to it. And there is a term called advect, where we take any data and advect it through time using another field. And in the case of point, you would apply some kind of transformation over the points over time and integrate that, and that's called advection. And with field, you can advect any field you have using a velocity field, which is a vector field. And in this case, the velocity field, the advection process would take that density field and apply the velocity to it to move it properly. So in this case, we're going to apply some velocity to move these guys in this direction, okay? So we're going to apply an exact amount of velocity that will advect or move this entire one here to this cell. So we'll have one here, and then it will be gone completely from here. But when we subtract the data, when we move the data, in order for this to be physically correct, in order for this data to be correct, this voxel here need to suck in data from their neighbor. So it's going to borrow values from all these guys, okay? So if we take this one out here, it's going to be left with 0, but it's not going to be satisfied with that. And the reason for that is because there is something called divergence that is always need to be met, and divergence has to always be equal to 1 in every single cell. And what that means is the difference between the incoming data and the outgoing data needs to be always 0. So when we move this entire one from here to here, it's going to suck in values from its neighbor to correct itself. So it's going to move this 0.5 here, so I'll get 0.5, and then if there is 0 here, it's going to move it as well. It's going to import that data, and then it's going to import, let's say, 0.2 to try and correct that with whatever is available, and it will import all of them here. So this guy will be left with 0, this guy will be left with 0, and this guy will be left with 0. And then it's going to trigger a whole chain that will touch and call every single neighbor, because when we move data from this guy into this guy, this voxel was not happy either, because its value changed. So it's going to start pushing data out. Oh, I have higher value. I have 1.5 now. It's not 1 anymore. So I need to get 0.5 out. So it's going to move its data to its neighboring voxels. And to solve this equation, this whole equation, Houdini has a node called gas project non-divergent, and it is what solves this entire equation all at once. And there is 3 different options, but we're gonna just use one for now. And each has different features and different advantage and disadvantage. We're gonna start just use an example here to illustrate what's happening. So basically, all we have to do to get a smoke sim going is have a domain. Okay, say this is my domain. Fill it with some density, apply some velocity that will to this data, advect the density field with that velocity to move it, and then solve the divergence to be equal to 1, so that every single cell keep its pressure normalized and its divergence equal to 1. And we're going to do those steps. Now, one other thing that is very important is this field. When we apply the velocity to the density, the whole system has a new velocity field. The whole system velocity itself changed, and we also need to advect the velocity field by itself. And those are the 2 steps. Basically, we need to advect density first, and then velocity by itself, and then solve the divergence. So div. So let's do that. And I have I have the teapot here. I'm just going to increase the domain so we have more room to see what's happening to the sim. So I'm going to make this bigger. There is an option for that in the offset, in the ISO offset node. And I'm going to, yeah, I think this is fine. Yeah, increase it by -2, -2, and 3 so we have more room. And I'm also going to convert this into a VDB volume so that it's faster. So I'm going to use a convert VDB node and convert this into a VDB field. Actually, let's do that afterward. Oh, it's truncating the volume. So that's fine. Let's turn this off And let's convert this into a VDB volume. And with VDB, to expand the boundaries, we need to use a VDB activate node. And with this guy, there's an expand feature here, and you can tell it how much you want to expand the boundaries to. Let's say it's too much. Say 50 voxels in every direction, and let's move. Yeah, we're not going to move anything. Or actually, we'll move the density so it's below instead of it being at the center to have more room. So we'll do that here with the volume sample. So I'm going to expose this, and that way we can transform the sampling position, which we're changing already. Let's take a look. Okay, let's move it by -1. Nope, we need 2, 1. Perfect. Okay, and let's move all this to the origin. So it's above the grid. Okay, now I'm going to call this out density. And we need to create a vector field. Now for the vector field, I'm going to just do something hacky. I'm going to take this name here and rename it. So let's see, with VDB. Yeah, let's take that, and then we're going to do use a name node. And I'm going to rename the density into val.x, val.z, and val.y. And this is how we construct a, this is a hacky way. Later we're going to learn the proper way. But for the time being, this should be fine. So I'm going to call these guys, and then I'm going to merge them all. And that will give me the vector field I need. Now it's duplicating the density, obviously. I'm going to put down a visibility node and hide all of that because I don't need to see this guy. And I'm going to scatter some points, and I will explain why. Actually, we'll do that in a second. So let's create a volume VOP, and we want to create some velocity. And here we just need to bind export val as a vector. And we're going to generate some noise. That's it. So here we'll connect P. And let's set this to 10. 3, 3, and 3. And it's a 3D noise. Okay. We want to visualize this, and the easiest way for that is to use scatter some points and use a trail node, a volume trail node. I'm going to connect the points, the val field, and now you can see we have that's how the velocity field looks like. And I'm going to copy this and call this out val. Okay, let's create a new DOP from scratch, and let's dive inside. Now we don't need any default node. We're not going to use the smoke object. We're not going to use the smoke solver. We're going to import the data from SOPs into DOPs. And the way to do that is we need first an empty object. And this is how DOPs work. It first initializes the placeholder, and then it fills them with data. It attaches data to them. So this is our empty object, and we're going to import that density field, and the density field is a scalar. So we're going to use a SOP scalar field to import data from SOPs. And let's connect that here. And we're going to use SOP dimension and out density. Okay. Now to visualize this, we're going to use a visualization node. And for this, we're going to use scalar field visualization. Let's connect that here. Sorry. Let's connect that here. Show and use smoke. And boom. Now we have our density. Now it's called scalar field. And that name is coming from here because we can attach data and give them any name we want. I'm going to call that density. And the next thing, we need to import the velocity. And for that, it's a vector field. So we need a SOP vector field. And we're going to do the same thing, use SOP. And then let's connect the velocity. And we're going to attach a we're going to attach a vector field visualization. And let's see, show guide, use streamers, and let's see what we get. Cool. So now it's displaying the data. Let's change it to use speed, and let's reduce the length, something like that. Cool. The volume is a little bit dense, so I'm going to lower the resolution a bit. So let's say 50. Let's give this a different color. Okay, cool. And I'm not so sure why the data is there. It's fine. I'm not going to worry too much about that. And the next thing I want to fix is each voxel is basically a box by itself, okay? And there is few methods for how it stores, how we can query data from this voxel. We can either query from the center, or we can query from the faces for the density face X, Y, and Z. This is only for density. And then for velocity, there is a few more options. We can either query from center, faces, edges, or corner. And the best method we can use is faces for velocity. And that's what the default should be. So we set that to velocity, to faces. And then the next thing is we need a multi-solver. And this node doesn't really care what you're going to do, what your sim is going to do. It's going to simply take this data and apply this micro solver. And this is where micro solvers can be connected. It can be anything. And then it will take this data and try to apply whatever solver makes sense to it. So in this case, let's say we want to blur the data over time. We can use a gas diffuse node, and let's say we want to blur the density field. Gas blur, not gas blur. I want to blur the density field over time. So let's hit play. Boom, it's happening. So it keeps integrating the result over and over, but it's not just applying it over the same data. The result is being re-injected back again, and that's what is being used in the sim. So it keeps applying it over and over and integrates the data. And we can chain anything. Let's say I want to dissipate this data, so we can use a gas dissipate node. And let's say I want to evaporate by rate. I want to evaporate 50% of this, and it will dissipate. See, now it's subtracting, it's evaporating that data over time, and it's incremental. And we can chain anything we want. But what we're interested in now is we want to make this look like a smoke sim. So what we need to do, as we talked about, is we need to advect the density using velocity. So we need a gas advect field, which makes sense. Okay, so we're going to advect density by val, and let's hit play. And I think I know why it didn't work, because the val data is not there yet. We can name this correctly, val, and let's hit play. And boom, now it's moving that density field using the velocity. Now, the other thing that we talked about is after we advect the density, we need to solve the divergence problem. So we need a gas divergence, gas project non-divergent. And there is these three versions. I'm going to use the second one. And each one of them has different features, and we'll learn more about them as we progress through the workshop. For now, they will all do the same purpose. Now you can see the result is a little bit different. The data is moving throughout. It's being integrated, and the voxels, the neighboring voxels, are also being affected every frame. But there is one thing missing. Now, when we talked about this, the velocity is advecting the density field. What that causes is the velocity field itself is going to change. And what we need to do is we need to advect the velocity by itself. So we need to first advect the density, advect the velocity, and then solve the divergence. So we need to advect the velocity field. So I'm going to copy this, and I'm going to advect val by val, and we need to take this on. And what this will do is going to copy the velocity into a temp field, advect it, and then put it back in the velocity, so it doesn't override itself. And then we're going to solve the divergence. Now with this, we should see a much more realistic, we should see a realistic sim. This is all we need to do. And you can see the smoke is behaving much more realistic now. Now, one thing I like to do is I like to add a little bit of force pushing this upward. So I'm going to go back to the velocity field that I have, and I'm going to add a constant to it to push it upward. So I'm going to add here, and then let's expose this, and it's a vector. I'm going to set this to 5, maybe 3, and let's see what happens. Boom, now the data is moving upward. And you can see how fast this is. Now obviously the sim is very low res, so we have to sim something a little bit more high res, but overall this is all we need for a smoke solver to work. Advect the density, advect the velocity, and solve the projection. Now let me create a smoke solver node, a smoke solver, and let's take a look at the values. So we have this temperature diffusion thing, we have a cooling rate, we have viscosity, we have buoyancy lift, we have buoyancy direction, and then we have other tabs for sourcing, which we'll take a look at, and then there is this advanced tab for min and max. So we don't have this section. Where is this coming from? This field here, we haven't seen it in any of the nodes. The advection method, for example, this is what we have been using. Now, if I go in this node, you can see I have this advection type. And all the smoke solver is doing is exposing the properties of the advection methods. And there is 3 options, each has different benefits, and the smoke solver is simply exposing the micro solver's properties inside of it. Same for all this, but I can't remember which one is this. That's because it's very important. Now this gas here, this min and max step, we haven't seen that in any of these nodes. And where that's coming from is coming from the gas substep node. What this does is you can plug this in here, and basically it will do, let me connect this, it will basically repeat these steps over and over and over. Now let me fix the order of things. So the first thing is the advect field, this one is the second, and this one is the third. Cool. Let's call them advect density, advect val, and that's the divergence. Cool. So you can see with this gas substep, this is the controls that were exposed in the smoke solver, and what we can do is we can tell it to solve this 3 times every frame by setting the min and max to 3 and 3. Now let me hit play. It's gonna be slower, obviously, but it's gonna solve the equation 3 times every frame, and this is the settings that is exposed in the smoke solver. Now if we set this back to 1 and 1, you can see it's much faster now. And the next, all these options are basically the micro solvers building up this guy. Obviously there is a lot of features for pumping. There's a lot of features for controlling the advection as well, and for sourcing the temperature and all the other fields. And you can see if we unlock this node and go over, you can see this is the advection happening. Surprisingly, the advection is happening first. The velocity advection is happening first, but we'll do a test and see. And all these nodes are basically what builds the smoke solver itself and what gives it the realistic behavior. And for example, the viscosity here is just a gas blur microsolver. It's nothing else than the guy that we used in the first to add a blur to the velocity field. That's all what viscosity is in the smoke solver, for example. The buoyancy, we're going to learn that in a second. And then there is a way to create rest fields, which we're not going to be using. And then this is what for making divergence free. So each one of these guys uses a different gas project non-divergent method. So this one is the gas project non-divergent, the default one, and then there is another one called multi-grid, and that's what the multi-grid option is coming from. And then this is mixed with the gas enforced boundary and then a gas feedback node, which hopefully we'll be able to understand as we progress through the workshop. And then this is for advecting all the fields that are available in the sim. So there's this density temp, density rest, diffuse temp. Sorry, it's blurring the diffuse, it's enforcing the boundary, and this is just microsolvers chained together to move the data and give it its realistic behavior. Now this is for cleaning custom fields temporarily, and then this is for doing all the sourcing. And the core of all of this is these three guys: the gas density, the gas advect val, and then the project. There's also the other project non-divergent, which I personally prefer the gas. This is the one I use most of the time, even with the smoke solver, and we'll learn the difference for that as we progress. Now, the other thing I wanted to explain is the gas buoyancy node, and what this does is basically gives buoyancy to the volume. And what I'm going to do is I'm gonna copy the density, and let's keep let's copy this, and I'm gonna import the same field, but instead I'm gonna give it custom name. I'm gonna call it let's call it temp. Okay, and what I'm going to do is I'm going to use a gas buoyancy node, okay, and I'm going to tell it that my buoyancy information is coming from the temp field that I just copied. Okay, we also need to advect this temp, so we have to make sure that that happens, and we have to do that before this guy. Okay, so let's advect the temp. And I'm going to use that in the buoyancy in this node. And the buoyancy is going to move the volume up. Let's set it to 5. And let me also turn off the this section. Let me turn off the volume force that is pushing it outward. I want to see what happens now. Let's hit play. Not so much happening. Let's try increasing this to 500. It's not moving upward. Let's see, why is that? Let's increase this. Okay, now it's working. Yeah, I needed to change the buoyancy value. Now look at this. It's taking the smoke upward, and that to me looks like an explosion. It doesn't look like just a simple smoke sim. And let's try this. Let's do a gas dissipate. Yep. And let's dissipate this field. So the field that I want to dissipate is temp. Is temp, and I don't want any control, so just temp. And the evaporation rate is going to be 0.5. And let's hit play. So what I'm going to do now is I'm gonna save the sim, cache it at a higher settings. I'm gonna change this voxel count to, let's see how much we have here, 140. Let's set it to 100. And I'm going to cache the sim and come back and I'll explain a few more things. Thank you guys for watching and see you in a bit. Hello everyone and welcome back. So now that everyone has a good understanding of how Houdini DOP works and the steps behind the sim, we're gonna go back to our wedging workflow. And this is a base file with the setup that we need to do everything we need. So what it does is we have a pyrosim. This is the DOP network. We have a smoke source, and this is very basic smoke source. I can show that. So just a sphere with the noise. And I have a pyrosim or a DOP network, and it's very, very basic. It's a sparse sim, okay, with the source, and I'm simply sourcing the density, velocity, and temperature. And then a smoke import, so we're importing back the fields that we want, and a post-process node to set up the look, a preview for this. And then this cache node is doing a trick. So right now it's erroring out, but the reason for that is because it's waiting on to read a file from the disk. So what this file is going to do is when we hit the sim or ask it to go sim, it's going to create these caches which are missing right now. Okay, it's going to create the cache, save it to disk, and then it's going to be used in a second process where it gets read and displayed. So the way it works, this node will kick in, it's going to read in the node, the smoke, it's going to run the calculation, this is going to import the smoke, and then this will save it to disk and display it in the viewport. So this file node here, this file node is set to read, okay? And the data is going to be written by another node. And I'm going to go show that node. So if I go to the out context, I have a ROP geometry node. It's pointing to this node, which is the cache to cache. It's going to write the file to disk, and then there's another step here called OpenGL render, and this is going to do capture and render an OpenGL, and everything is set up so that the data looks like this. So for example, I have this file, okay, smoke dissipation 0.1. It creates a folder, it saves the file to disk, saves the geo file to disk, and then it does a viewport render. So if I play it, if I play it, this is how it looks like. Okay, and then the file, I improved it a bit so that later used a different color, and I'm highlighting the nodes or the text that I'm changing. I believe in this one I'm simply writing a test, like the node name or the file name, and that's it. So this is the initial workflow. What we can do is we can always change these two nodes, and that would be our sim. So let's say I have a fancier emission and I have a more complex sim. It's all the same silhouette. Okay, it's all the same platform. And then this cache node, once the file is saved to disk, it will be able to read it. And then the info is really, really basic. I have a text file, so a text node or a font node, and it's referencing specific attributes from the sim. And we can change this. It is changing, and every time I add whatever I need. So for example, here I'm referencing the division size, the min-max, the time, the advection method, all of these things, all these settings that I care about are being put in display, and we can just change whatever we need. So if I wanted to move the text here, I can do that, and it is parented to the camera. So whatever the camera, wherever the camera is going to be, this text is going to be always displayed on top of it, and that's the workflow. And so I save it to disk, and then let's say I have another control I want to test. Let's say I want to test the expansion of combustion, just to test. I can then go in and go to the Pyro Solver, tick on the divergence or expansion, and tweak this value. And make sure that this is being read and used in the display setting, and that would be my file. And when I go and hit render, not this one, but this one, when I hit render, it's gonna start the sim, respect this node, and then render it. And that's how everything is being done for all these tests. Okay, and I will give, I will package all of these settings as well as the HIP files, and this should build a nice library for all the settings that you need. And if, for example, the viewport is not the best, you can always open the HIP file and see what it does. In the next video, I'm gonna go over some of these and explain them in more depth, and then we're gonna dive into all of these wedges and then start doing some sims. Thank you guys for watching, and see you in the next video. Bye-bye. So the first thing we did was to fully understand how the smoke solver works, and Side Effects added a lot of new things, not just the combustion model. So there's a lot of new things, and we wanted to see how each one of these affect the result. So they have a new advection method, either disabled, single, or double, and each one of them has a different sim time and different result. So in this case, I wanted to see, change this. So in this case, I wanted to see how that affects the sim. How is it going to look like? And then there is a reflection amount as well that I'm changing. And in this case, the advection reflection is off. The advection reflection set to, I believe, the second option. And then the same here, but with a reflect amount, a different reflect amount. There is difference for sure. But with this example, it's hard to tell what is happening. You know, it's really hard. We have to have a high res sim, but that is something that drastically, I wouldn't say drastically, but it affects the quality of the sim. So it would be an option that we would look for. Unfortunately, the sim time is a bit tricky to get. So I had a Python script. I wrote a Python script that stamps the time frame this viewport capture happens, but it's not being updated every frame. So when I'm curious about the sim time, I have to go in and check the file stamp, the file time stamp, and compare the first frame with the last frame, and that gives me an indication of how long it took. But as of now, unless you use a farm or a render management tool, we're not going to be able to easily get that information. So the next setting I tested is the ambient lift. And again, everything is explained, everything is an option in the combustion, in the smoke solver. So this is the ambient lift. You can see the higher the value, the less the smoke goes up. And this is what I was talking about by the ambient. What is the normal range? Okay, if it's lower, if it's a low value, then the smoke is going to go up very, very quickly. The higher this value, the lower the smoke is going to rise, and if it's too high, it's going to go negative. I find it unintuitive. It's hard for me to tweak. I prefer one value. It tells me the smoke is going to go up or it's going to go down. End of story. I don't like this, balancing these two things with sims. It's really, really hard. So I will show what I've ended up doing at the end, or when we get to it. So buoyancy scale. It's very obvious. The higher, the faster the smoke is going to go. The higher the smoke is going to rise. So this is the same as before. Density. So this is in the source. I wanted to test how the source affects the final result. And in this case, I'm not seeing a huge difference. Okay, I'm not seeing a huge difference in terms of the sim and even the final output between a value of 1 and a value of 100, which is a bit weird to me, but I guess that's how the new solver works. There is difference. There is difference between these two, top left and right, but it's not as much as I would have expected it to be. And I'm gonna do something very quickly. I'm gonna change the player to use the Deja Vu. This will allow me to use the mouse, the cursor. I wasn't able to show this. So the next one is the dissipation. Okay, so value of 0.1, value of 0.25, and a value of 0.75, and then 0.5. You can see how this clipping is it has a weird clipping. Same here. The reason for that is because that sparse or adaptiveness thing, it's only accounting for the density field. If you don't have a density field, everything shrinks. So that's something we have to be aware of. But the dissipation is very obvious. 0.1, 10%, 25%, 50%, and 75% every frame. And then the remaining displays as simply the temperature field. The next one is the disturbance. Again, these are not in order, but they're all important settings that we need to test. So this is the effect of the disturbance node on the sim. And looking at all of these, I actually see a lot of potential here. And again, we're talking about simple sims here. We haven't started doing anything fancy yet. I like how this one is looking. And I just have a simple sphere emitting, and we're getting tons of details. Now, there was one gotcha that was confusing all along in all these sims. You can see some stepping. You can see some weird stepping in the beginning or in the edges of the sim. Okay, you can see it in various places. You can see this striping. In some cases it worked really well. In some cases it helped to add some details. But after some more investigation, I realized that the stepping is coming from the sparsity feature. And after days and days of testing and trying to fix that, and talking to side effects, there's actually no way to fix the stepping. And in many cases where the smoke is expanding or moving very, very quickly, the sparsity feature is going to give you that stepping. They don't have a fix for it at the moment, and unfortunately, most of the final sims or most of the tests that I did not have sparse on, because that they inject this clipping or this edgy stepping effect. And you can see it very, very clearly here. You can see how it's going to start, and it's always there. In some, again, it helped in some cases, but I don't think it's natural. And we need our mushrooms. We need to have that simple mushroom behavior so that we can start attacking it and solve that problem, instead of having, all of this, because this will ruin our plan if we wanted to add details. So yeah, that's a note about the sparsity. Okay, so diff size, this one is just a single test. The reference temperature. So we tested the ambient lift, and now we're testing the reference temperature. And again, this is the threshold. It compares the ambient versus the reference, and based on where the smoke is at, it either moves it up or moves it down. And again, I found it unintuitive for me. Maybe you guys can figure out how to tweak these values and find the relationship between them, but I find it a bit hard, so we're gonna rely on one value. And in my workflow, I'd rather have one value that I change and get a result quickly, rather than having a two value, especially if their range is quite wide. It's much harder to tweak. So one value, one result. This is a test with shredding. And again, please be aware that there is a stepping effect. The stepping effect is coming from the sparsity, but the shredding is also working. So this is a shredding of 100, and to me, I like seeing the huge difference between the extremes. And I know, okay, it can be somewhere around these values, but we can never go high. And the shredding is actually quite tricky, because we can actually change the data inside the sim, so we have to be very, very careful with this control. Cool. So that's another micro solver. substeps. So substeps is number of iterations the sim goes through. So in one frame, the default is 1 1. Here it's 2 2 and 4 4. So these two comparison basically, or these two. And in this example, it's helping with that stepping. But again, if we're gonna be increasing the steps to 4, then it's better to have a substep of 1 and turn the sparsity feature off. You know what I mean? Because if we're gonna sim 4 times more, then it doesn't make sense to have the sparsity feature on. And that's what I came down to. The discussion from side effect was, if you're gonna use sparsity, you have to increase the substeps. And so you're put in the situation where, okay, I can turn on sparsity, which improves the speed, but now I need more substeps. So it goes back to square one, where the sim is just slower, and it's easier to deal with a sim at a substep of 1 and no sparsity. And that's what I ended up choosing. But it may have changed, so maybe they did some work. I haven't tested it with 18.5, and I haven't seen anything related to this, but maybe there's an improvement. So this temp acceleration attribute, I'm not so sure what it's doing exactly. I'm assuming it's how fast the sim is gonna reach certain temperature, or the temperature field is gonna reach certain value. And but I'm not so sure as to what is happening in these sims, honestly. I don't see a huge difference, if none. So maybe that's something we need to investigate. Oh, sorry, I know what this is. I forgot. So we have, so they added these options in the ejection, and the operation mode is called pull. And it has an acceleration strength and a deceleration strength. I have not gotten anything out of these 3 options. The pull mode is probably the most confusing mode that I've tested. And what I've gone through rigorous tests and did so many things with it, but the simplest one is to simply use an add. I know I'm adding temperature, and this is my value. End of story. The other one is basically pulling in temperature and multiplying it by a certain value under certain conditions. I don't want that. I don't want anything interfering with my operations. I have a temperature, I want to inject. That's it. So that's what the temperature acceleration and deceleration are for. The next one is the time step. Very obvious. The lower the time step, the slower the sim is going to be. And then turbulence, quick test with the turbulence value. And this is again only testing the overall magnitude. We're not going deeper into each one of these, which we've done later. So you can see the effect of the turbulence on the sim. And then the last one is the velocity, and this is the velocity of the source. So the faster, the stronger the velocity, the stronger the emission is going to be. And this is from the source node. Cool. Okay, guys. Well, this is some of the tests, and I think it clarifies a lot of things about the smoke solver. We're going to continue in the next video studying some more and get some sim started after that. Thank you so much for watching, and see you in the next video. Bye-bye. Hello everyone, and welcome back. So now we're going to take a look at the combustion model that ships with Houdini 18 and 18.5. And this tab can be located in the Sparse Solver under the tab called Flames. And you can see it's much simpler now. It has 3 sections: smoke, temperature, and expansion. Now, what these are for, the first one is when we have data coming in from the external source, and we're gonna see what this data is, we can tell the smoke or the solver to emit more smoke based on that. This is not the same as expansion. Emitting smoke, let's say you have fire and that fire is super hot, and after the fire dies off, we get smoke left over off of that. So that's what the smoke is for. The next part is temperature. So as I was explaining before, you can have a flame, and then that flame causes the smoke around it to be more hot, and that's the temperature field. So the temperature field goes beyond the flame field, which is the source. So it gets advected with a sim, and it can expand. It can go up and works with the solver and the buoyancy system and everything. So that's the temperature. We can take this data coming in and say we want to make the temperature go higher or lower based on this incoming data. And then we have expansion. So the expansion will cause the smoke to actually expand. And this is what we want for explosion. So explosion will generally expand very, very quickly in the first couple 10 frames, or the first 10 to 15 frames, and then stops and stops the expansion and continues to rise or dissipate and evolve. So that's the expansion feature. Now with the source, with the volume source, there is a new interface where we can basically source in data, and then we tell it what field it goes into. Now this new combustion model, I'm going to go in and turn expansion, and I'm going to hit play. And you can see nothing is happening. I'm going to increase it to 20, and you can see still nothing is happening. So what the solver is looking for is a field called flame. So the new combustion model requires flame. Before it used to be heat and burn and combining all these things to produce expansion. Now it's much simpler. Now it's one field, one result. So what I'm going to do is I'm going to copy the density field, and I'm going to inject it into the flame field. So I'm sourcing density, and the target is flame, and the operation is add. And we're gonna leave everything is the same, and if I hit play now, you can see that it's expanding, and this value is really high, and there we go. The solver is now reading that flame attribute or the density attribute information, and it's being used in the as a flame information, and that's what the solver is doing. It's reacting based on that information. So I'm gonna lower this value to 0.1, and I'm gonna see let's lower 0.05, and then for the temperature. So right now we don't have any temperature being displayed. So let's do let's display the temperature. Measure. I'm gonna set this to 1. Temperature. I'm gonna leave it to clamped ramp and black body. We'll just go with this for now. So let's hit play, and we don't have any temperature. Let's hide the smoke completely, or set it to 0.1 and increase the temperature to something really high. We don't have any temperature, and the reason for that is because we're not creating any heat. We're just using the flame, which we're not displaying. So to get the temperature going, we need to turn on add temperature, and now we're gonna see that the flame is emitting heat, is causing the temperature to react, and that's causing the smoke to rise up. So I'm going to change this to 1, and if I hit play, you can see we have pardon me, let's change this to 10, let's change this to 10 as well, and now we have the flame running through the combustion model, and we're getting heat, and the smoke is rising up. So let's add a little bit more expansion and a little bit more temperature, and let's see what happens. So now the smoke is gonna pardon me, is gonna go up faster. We're gonna have more temperature, and that's gonna evolve in the sim and work nicely. So that's basically how the combustion model works. And we've run a lot of wedges, obviously, because we want to test everything. And in the next video, I'm going to dive into all of these. And to sum it up, as I was explaining, the control, this one, the merge mode, I'm not super fan of. You guys can try it, but I prefer to use add. It's easier, it's simple, just have a value, it gets added. And then the flame range is basically what value or what range you're going to capture from this flame. Okay, so we can say I want to emit temperature from the really hot flames, and that would be, instead of using 0 to 1 range, we use half of it. We use from 0.5 to 1. Same for the expansion. We don't want the sim to expand everywhere there is a little bit of flame or there's a little bit of heat. We can narrow this down to say 0.8 and 1, and that means the really hot flames will expand, will cause the smoke to expand, but everything else will be fine. And then we have this curve which we can use. So for example, we can leave this to 0.1 and we can just play with the ramp like this. Cool. So we're gonna take a look at the results in wedges and learn more about this. Thank you guys for watching, and see you in the next video. Bye bye. Hello everyone and welcome back. So let's take a look at the combustion model and all the controls that we have, and this is going to be primarily the smoke, temperature, and expansion. And this is not in order, but they all are related, so the order of reviewing them doesn't really matter as long as you guys understand what we are going to be looking at. So this one is the expansion range minimum, and that would be this one. So let's say I want to test, I'm going to turn off the remap. I'm going to test the range minimum value. This is, and see how that affects the sim. So here, that's what this result is for. Same as other window, I'm going to move it. So we have a range min of 0.25, range min of 0.5, 0.75, and I believe I'm going to open it with a different player. Sorry about that. And this is a value of 0.95. So basically, we're telling the solver to use more or less of from that flame field, and the lower the min value, the more expansion we're gonna get. And this is reaching to a point where it's just hitting all the limits and the sim is going crazy. These ranges are reasonable and getting nice, and we're getting decent expansion. You can see the difference in volumes, how much smoke we're getting. And this is not extra density, this is the smoke expanding. This is what the divergence field does inside the solver. And so that's the effect of the min range. I think a value of 0.5 is always a safe range to use. So that's the result of that. Let's take a look at the another setting called the expansion rate, which is very obvious what it means. It's how fast or how much expansion do we get. In these examples, obviously a range of 1, a value of 1 is already giving us a lot of expansion, and then just going higher is going to explode the sim. So this is an expansion rate of 2. You can see a lot of smoke happening here, and all these clipping boxes are caused by the tiles system or the sparsity system. We can definitely get the sim to behave like this if we wanted to, but for the testing purpose we don't have to go this high. I mean, we don't need this. We don't need these results to look good to understand that we don't have to go this high. So value, maybe the safe range would be 0.1 to 2 depending on what we're doing. Okay, the next one is the add strength, and this is for the temperature, and this is the add temperature strength. This one is 1, this one is 1. The strength from the source, so this one is 100, in the solver. So the default setting is like this. This is the value that I'm testing. Okay, turn this off. So the value is a strength of 100 and a strength of 10, and the pull method is 10. And you can see there's difference between these two results. There's more temperature here, but because the temperature field can only cause the smoke to go up, the difference is not that major between the two results. And this is another thing why I don't like having multiple factors for the temperature. You have a pull method, you have a temperature amount, and you have a strength value. So for me it's a little bit confusing, and I'd rather have one value, as I said before, and just control this. So, but it's up to you guys. So temperature amount, obviously what this is the main multiplier, and we started off with a value of 0.1, and this is a value of 1, and this is a value of 10. Again, we're not adding more smoke, okay? Making the smoke hotter does not add or expand the smoke. We're simply causing it to raise up more, okay? And this is just the sim behaving. So in many cases, for example, because see how much nice movements we get by having just a broken up temperature field that causes the smoke to swirl and go up. For example, when you have a sim and you want to get a lot of nicely swirly movements, but you're gonna render it, let's say you have a creature landing on the ground and stomping on the ground. You can use the temperature field to get the nice movement that you want, but you don't have to render it. This is something I do all the time. So you can use this data to tweak the sim and get the movement that you want, but you don't have to render it. You can have hot smoke and cause it to rise and swirl, and you don't have to just display it in the viewport or in the render. You can render the density field only. Cool, let's move on. I have the temperature max. So this would be, let me find what the setting is for. So the temperature range min and max. So this one is range max is set to 0.25. And what we're doing is we're simply using more of the flame. So if I have a data, the flame information that goes from 0 to 1, we're telling it to use the lowest range between 0 to 0.2 and just use all of that into the temperature, which will make the smoke get hot and go up very quickly, even if there is a little bit of flame. Okay, so that's what clamping it and doing this lowering the range min value will do. A better value would be, a safe value would be 1, and then maybe we can play with the min a little bit more. So the next attribute is the range min, and again, this is simply changing the range of how much data from the flame information we are using to make the smoke hot. Okay, and the higher the value, the higher the range min, the less we capture from the flame, the less heat we emit from the flame. Okay, and then temperature remap curve. I don't think I took a picture of this, but I'm using, let's see, yeah, we can look at the file later, but this is, actually I can do it now. So combustion add temp remap. I'm going to open the file very quickly. So this is just a variation of remapping the data. So instead of using a linear curve, I'm just doing this crazy ramp. And it doesn't have to be this. This is just to see how it would affect the result. And honestly, I don't see a huge difference. I don't see that I have to do anything fancy here to get the result that I want. And in most cases, I've simply used a normal ramp or a linear ramp or just a little bit of tweak there. We don't have to do anything fancy. Okay, and then the next one would be the smoke amount, which is this tab, emit smoke. So the amount 0.1, 1, 10, and 100. And if we look closer at the sim or at the silhouette of the sim, it's not that different. We're not getting more smoke. It's not expanding more. It's just getting denser and denser and denser. And if, for example, we have other controls that are or microsolvers that are being driven by the density field, those things will change. But the overall sim is gonna be the same, in the same range. It's gonna look similar. Okay, this is not emitting more smoke. It's not gonna cause it to rise up more or behave in any way different. So these two sims are not that different. It's just the display or the information of the density field that is changing, but the sim is not changing too much. So that's what the smoke amount is for. And then the range min and the range min and max. So how much from the flame field we're gonna emit, and I think I combined these two. I combined the range min and max, and it's very simple. The 0 to 1, we can just say I want to use the super hot flames to emit smoke or make it denser. I want to use everything in the flame, even if it's a tiny bit hot, I want to use it to emit smoke, and that's what these controls are for. Smoke remapping, and then the lifespan. So this is the flame lifespan. Okay, this is not the cooling rate for the temperature. There's another setting here under the simulation called cooling rate. This is not the same. The cooling rate affects the temperature. Okay, the lifespan affects the flame field. So we have a sim, we're importing data from the solver and we're injecting it into the flame. That flame gets infected with the sim. It moves up because of the temperature and everything, but we can decide how big the flame lives. And so that's what this control is for. Lifespan of 2, lifespan of 4, lifespan of 10. You can see it's going up further and further, which will result in changing the sim overall. And I think that's pretty much it. It's really simple to tweak these settings, and the majority of the work is going to be in the solver, getting the work in the solver and then adding micro solvers. Thank you guys for watching, and see you in the next video. Bye bye. Hello everyone, and welcome back. So now I want to create a simple smoke simulation and cover a few things while doing this example and show how to create everything from scratch. So I'm going to create a geometry node, create a torus, and set this to 0.1. The idea is I want to have this ring or a portion of this ring start sweeping, going up and down, rotating, and we're going to use it to emit smoke. So let's delete a portion of it. Let's just delete it by hand. I don't need the full circle. Something like this. And I'm going to use a polycap. We need the geometry to be filled. Okay. And I'm going to use a VDB from polygon and convert this into a density field. And I'm going to take on fill interior to make sure that we have data inside. I'm going to use a volume wrangle node, and I want to increase the density. So I'm going to process the density field and say I want it to be 10 times denser. So that's what we have. And let's take a look at the resolution. We're quite low at the moment, 12.5 by 5. I'm going to lower this to 0.0604. And I want to have this rotate and go up and down and emit smoke. So I'm going to put down a transform node and use a sine and cosine function just to have it go in various directions. So I'm going to have it go up and down. So $sine of frame multiplied by 2. So now we have it do this. We can increase it to go up and down faster. Okay, and let's have it rotate. So we're going to have it spin all the time. $F multiplied by 5. Let's see how fast this is going to go. Okay, and I want to have it rotate like this as well. So let's add some rotation on the other axis. $frame multiplied by 2, something like that. Cool. So what we want to do is we want to use this to emit smoke. So I have everything I need. I have a density field. That's all I need. I'm going to create a null and say out density. I'm not too worried about having the wedge system. I just want to show how to use the how to create a simple sim and get everything going, and explain how to save data and do all the steps needed. I'm going to create a DOP network called a sim. And let's copy. So if you hit Control C, it copies the path to the data. And I'm going to delete the output node. I'm going to create a smoke object sparse. A smoke object sparse. And I'm going to create a smoke solver. I just need smoke for now. And we're going to use a volume source. Okay, I'm going to plug this into the sourcing attribute, sourcing input, and this is in the first input. I'm going to paste the path for the data, and by toggling between one of these, so it looks like it's set to source smoke, but it's not. So I'm going to go back and forth between collision and source smoke, and that will set it up to import the necessary data that it would expect. So right now it's looking for temperature, density, and val. We don't have all of this. We just have density field, and we're going to go with that. So let's hit play and see what is happening. You can see the smoke is being drawn in that area. So, but it's not expanding. Oh, sorry. I'm going to use a smoke solver sparse. Sorry about that. And that's why I was confused, because the source is the second one. So smoke solver sparse goes with a smoke object sparse, and if we hit play now, if we hit play, we should see the smoke expanding nicely. All right. Cool. So we have a density field, and what I want to do is I want to add some temperature to this. Okay. So what I'm going to do is I'm going to use a name node, and I'm going to take the density field, rename it. Actually, let's use this one. And we're going to take the density field and rename it to be temperature. Density to temperature. And I'm going to merge all of it. And now we have density and temperature field, and they're both identical. Okay. And that's not what I want to do at the moment. I want to change the temperature to be different than the density. So what I'm going to do is I'm going to use a volume VOP. I'm going to dive inside, and I want to add noise to the density field for now. So let's put down a sample gradient as volume sample, plug in the position, and we want to sample the first input. And I like to use primitive name because I can easily it will always be consistent. If I change the data or the number of primitives, this will always work. So I'm going to add a turbulent noise. We want to offset the position of the density field. Like that. It's a 3D noise. And we're going to use this as the position. If I plug the volume sample to the density, nothing changes, obviously. So I'm going to plug this here. And now we should have noise. But right now what's happening is we're seeing the temperature field as well. So to hide it, I'm going to use a visibility node, and I'm going to say hide. Just leave it as the default. It hides selected primitive, which is everything, and now we can see the noise result working as we wanted it to do. Okay, so let's increase the frequency like this, and I don't want to break the density field a lot, so I'm just gonna do these tweaks, and then I'm gonna also do the same thing for the temperature field. So I'm gonna copy this, copy these two, and we want to add temperature. So you can see if I unplug it, it's displaying the default density. If I plug it here, we see the density deformed. If I plug it here, we see the temperature deformed. But because they are the same, it's looking, it's the same data, it's looking like the temperature is similar to the density, but it's not. So see, this is the temperature field and this is the density field. However, I don't want the temperature to be present when there is no density. So what I'm going to do is I'm going to multiply the density with the temperature, so it masks the result, and I only get temperature where there is density. Okay, and then what I'm gonna do is bind export this to update my temperature field, this one, and this is going to be my new temperature field. And then we have the density field updated as well. I'm going to increase the resolution a bit more, so 0.2, 0.1, so we have more accuracy in the data. And now if we animate this, sorry, if we animate this, we have the result that we want. Cool. Let's go back into the sim and take a look. Oh, it's going much faster. Sorry, it's emitting smoke, and the temperature is really high. So, oh, the default is add. Sweet. So in some cases, when you use the shelf, it's going to use the mode poll. If you want to use that, that's perfectly fine. I prefer to use the add mode because it's easier. And I'm going to scale the temperature right now because it's too high or too hot. So if we hit play, we get set temperature and it's rising. Cool. So this is with using just the smoke solver. We're not adding any expansion. We're not adding anything. So what I'm going to do now is I'm going to increase the resolution of the sim to 0.6. And let's hit play. And you see how in the beginning it did not capture where the object is. It did not emit smoke. Pardon me. And the reason for that is because the bounding box was not anywhere near this area. So what I'm going to do is I'm going to just expand this by hand a bit, or move it to where the data is. And now if I hit play, it's already located in the correct area, and this is our first example. So I'm gonna stop here, and we're gonna continue diving into this and explore everything within Houdini 18, and hopefully this will be a very good start for everyone to get going with the workflow and how to use the Pyro Solver and the Smoke Solver. Thank you guys for watching, and see you in the next video. Bye bye. Hello everyone, and welcome back. So we have created this sim here, and I'm gonna hit play, and nothing is visible. So let's go back inside. Let's create a DOP import fields, and we can use a preset. I'm gonna just tell it to use smoke and drag this node, the network, and then I need to copy the sparse object, and that's my DOP object. And now we should see the data. So what we're doing now is we're simply importing data from within the sim, and we don't need velocity, we don't need rest data, we don't need CD, we don't have them. So this is all I need. I need temperature and density. And as we continue through this workshop, you guys will realize that the viewport I use makes things look a bit nicer, or actually a lot nicer than the normal viewport in that comes with Houdini by default. And the main reason for this is because I have Asus installed, and I'm gonna provide a video on how to install Asus. If you're curious about that, it's a LUT system for color correction, or for being able to render in a different color space, which is similar to the S-Log. This will expand our ability to render, and it will give us way more control over in compositing. And the main issue with the default viewport, it's clamped, and it's limited to display things between 0 and 1, and it generally looks pale like this. So this is the default if I didn't have the Asus Workflow installed. And what I'm gonna do is I want to make this look as good as possible, and let me increase the sim a bit so we have more data to display and work with. And let's hit play. Okay, And I'm going to use the volume viz node, volume visualization. And I'm going to say I want to, this is my density field, and this is my temperature field. Okay. I'm going to set it to 1. The color, the emission color field is also the temperature. And I'm gonna say I want to use a black body ramp, so it looks like fire basically. I'm gonna change this a bit. And I'm gonna change this as well. Cool, so this is my range. And then we have density and we have temperature being displayed. We don't have any lights in the scene, so I'm going to go up and create a distant light or a light. And it can be a point, can be whatever we want it to be. I'm going to put a distant light and just use one light for now. That's all I needed. And I'm going to go back inside and increase my density value. So just the viewport, this is not changing the density or anything. Okay. And I'm gonna go and increase the temperature field. You can see it's clamping very quickly, and this is the main issue with Houdini native viewport or just rendering in sRGB. If I switch back to the Asus workflow, it's gonna look very different. So this is what it looks like in sRGB mode. And what we are able to do is we can render or display way more data. You can see by increasing the temperature to 10, these values are actually much higher than 1. Okay, and this is crucial to displaying the temperature field, because we don't want to be limited by 0 to 1. We don't want to be limited by that range. I can even go higher and it still looks good. If I go back to the raw and no Asus, you can see how terrible it is. So that it's very important to have this part. You can watch the separate video. I'll call it bonus Asus. It's from a different workshop, but it should cover everything needed for you guys to understand how to install this. We're gonna need it later anyway. So if you want to make nice viewport captures, you can install it now. Okay, let's go back. So we have a temperature field and that we're displaying, and we have a density field, and we can remap the temperature range. So instead of using 0 to 1, which is the default, I know that my temperature field, for example, goes between 0 to 1000. I can simply put that here. Now it's very important that you always have these two linked, because we want the color to be driven from exactly the same information as the temperature. Okay, so these ranges needs to be the same, but this is not obviously correct, so we're going to go back to 1, which is closer to what we have. I can even lower this because I know the temperature is very low, but we'll keep it for now. Let's go to 25, and this is our simple sim. And I don't know why it's doing this. Flat shaded, cool. And I'm gonna hide everything. And this is our basic sim. So the next thing I want to do is I want to show you guys how you can display high quality sims. And I'm gonna increase the resolution even higher. So how much do we have here? I'm gonna increase this even more, just to have more data in the source, more resolution. I'm gonna increase this to 0.1 as well, and let's see what we get. It's gonna be slower, obviously. And let's wait. You can see this blue line here, and what's happening now is the sim is caching to memory. And it's gonna quickly start erasing this range, and the reason for that is because we hit the cap of how much memory this node can use. Okay, and I'm gonna show where this this limit is. You can see now it started erasing because just to keep this in memory, it's reaching the limit that it has. This limit can be found here. So under simulation, under cache, you see cache memory megabyte is 5000. When I sim for final, I set this to 496. 5000 is fine, and we don't want it to be 0. We don't want to turn off cache simulation. We want to have 5 gigabytes, 6 gigabytes, or whatever you have available at your machine. Obviously, the higher the more memory the sim is going to consume, but we want to give it a little bit of padding, a little bit of memory, a couple of gigabytes for it to breathe. We don't want it to turn off caching properly, because this actually speeds up the sim and gives us more accurate result. So at this frame, we have a lot of voxels. We have 75 million voxels, and we are not seeing all of it properly in the viewport. So I'm going to turn off the temperature, and this is what the smoke looks like. Okay, even though it's very smooth, there is a lot of voxels in this sim, and to display everything in the viewport, we need to change this value to 1024. Okay, now this does not mean we are actually getting 1024, because there is a lock or another control for making sure that we're getting the best viewport we can. Now I'm going to show the NVIDIA. Let's watch. 1 second. NVIDIA SMI. So this is NVIDIA memory usage. Okay, I have a 2080 Ti. I have 10 gigabytes memory, and currently we are at, not this one, we are at 600 megabytes. I'm gonna keep this on. I'm gonna press the D in the viewport and go under texture. You see this limit resolution? This is the gatekeeper. This is what's locking the viewport from displaying the 1024 resolution. And you have to be aware that if you unlock this, you will quickly fill the memory, and if you don't have a lot of GPU memory, then the Houdini is going to crash or freeze. So I'm going to unlock it for now. I know this is fine to display. And then the other thing we want to do is full HDR. We want to display everything. We're going to pass all the data, raw data, to the OpenGL so we can get the best result. There's also HDR rendering under the scene setting. This is very, very crucial, because we're going to be rendering 32 bits to display all the temperature data in the viewport and be able to do nice captures. We have to make sure that we're doing HDR rendering. Now these changes did not reflect in the viewport yet, and what we have to do is we have to either close it and open a new one, or we can do this. We can go back and forth and look at this number, 424 now. If I go back, it's 733. And now we're displaying, and you can see the resolution is higher. Okay. If I go back to 256, this is what we were looking for, somewhat what we were looking for. And then if I set this to 1024, then now we are directly telling it to display this. Going higher to 2048 does not make a difference. 1024, I find it to be enough to display everything the sim has. But again, we have to be very, very careful, because it can easily eat the memory. And now it's 1800. And let's display the temperature. And now it's more, because it's displaying a separate field. And let's change this to 10, 5. And that's how you get, that's how you display a sim in Houdini. Okay, so I'm gonna go back to, I'm gonna turn this off. And by doing so, we are still seeing the old result. And if we have this off and we leave this to 0, or we turn it off, it actually goes with the highest resolution. So I'm gonna turn this back on and leave it for now. So it's like a gatekeeper or a safety lock on the OpenGL so it doesn't crash. All right, so we imported the sim. We use the visualization. Again, this is not shading, not rendering or doing anything, just viewport, and we can use any light we want. So I generally do like a simple rim and fill, and I change this to have a blue color, and I lower the intensity to 0.3. So we have like a nice fill on the sim. And then I'm gonna go back again, put down a raw output, and I want to cache this to disk. So I'm gonna cache it to where the file is located, sim, and I'm gonna call this live because we're caching it live. And I'm gonna call it quick or ring.v1, and I'm gonna put the frame number .f, and I want to cache 50 or 60 frames, and this is fine for now. So I'm gonna hit save to disk, and then we'll continue in the next video. Thank you guys for watching, and see you in a bit. Bye bye. Hello everyone, and welcome back. So the sim has cached, and I'm gonna look at the time frame. So it started at 12:35 and it finished in 3 minutes for 60 frames. Pretty good. I'm gonna put down a file node, and I'm gonna paste it here. And now we're reading the data back from disk. It's actually quite high res for this sim. And I'm gonna copy the volume viz because I can use it here. And that's how the sim looks like. I'm gonna increase this to 25, maybe this to 3, yep. And we can go back. And because of the high resolution sim and the viewport OpenGL, we cannot play this in real time. Okay, so what I want to do is I want to compress this data and convert it to VDB. So the first thing I'm going to do is a VDB convert, because we use the Houdini native format and it's a geo.se, and we can store VDB volumes in a geo file, which is the Houdini native extension, but for rendering purpose we need the extension file to be VDB, and it can only contain volumes. So I'm going to import this data, plug it into a VDB convert node, change it to VDB. And now if I middle click, you see I have VDBs 2, and before it was volumes 2. Now this data is raw. It has 32 bits and it is exactly what the sim needs, but we don't need all this resolution for rendering. We can save it as 16-bit float, and that will reduce the file size quite a bit, and this is one way of optimizing the data. So I'm gonna put down a primitive node and go to volumes and adjust compression. Sorry, not volumes, VDB. I'm gonna turn on write 16-bit floats, and I'm gonna compare side by side one of the frames. I'm gonna go to 60, and I'm gonna save the original. I'm gonna call this original.vdb and current frame. Save to disk, and then original compress or 60, and then save to disk. And if I open, you can see we went down from 170 megabytes to 100 megabytes. This is a huge saving. Instead of 17 terabytes, it only takes 10 terabytes, for example. So that's something we always have to do. And as part of the caching workflow, whenever we import a sim, I will always plug it into these two and make sure that I'm only saving the data that I need. In this case, I only saved density and temperature, and that's all I care about. That's all what I'm going to use for rendering. And there's no visual or noticeable difference, if none, between rendering the original or the 16-bit float. It's not like we're going to lose any data, but we're going to save a lot on disk space. Alright, so that's saving and optimization in a nutshell. Thank you guys for watching, and see you in the next video. Bye bye. Hello everyone, and welcome back. So now we're going to take a look at the Pyro Solver with the combustion model and see what we can get for this effect or using the same source. But I wanted to point out that we were able to get the temperature to show up, as well as the smoke to behave like a fire. And this is something a lot of people don't realize, is that you don't have to use the Pyro Solver to create fire or simple smoke simulation. You can get a lot of things done with the basic smoke solver and adding microsolvers. And in fact, what the Pyro Solver is, as I explained before, is simply, let me lower the resolution to 0.6. What the Pyro Solver is, it's a smoke solver plus this tab, this flame tab for the combustion model, and then this shade tab, which is basically a couple of or 4 microsolvers, and that would be the dissipate, gas dissipate. It would be the gas turbulence node, the shred, and the disturbance. So this is what the Pyro Solver is made of. And we can get the fire and that look to work nicely with just the smoke solver and by utilizing the temperature field, because the smoke solver will also account for that. So let's go back up. I'm going to copy this and call this Sim Pyro. And we want to change and use the Pyro Solver. So I'm going to, I don't know if I need a Pyro Sparse. Yeah, so the same object and the same source. Okay, and I'm not going to use any of this. I'm going to move this away, and we should see, if I turn this off, we should see now the exact same result as before. Sorry. So if I hit play, we should see the exact same result as the smoke solver, because we're not using anything from this yet. So let me change. It looks like the temperature is being used a bit higher than the smoke solver, I think. Actually, yeah, it's rising up faster. So maybe the default, yep, you see the default is different between the two. So we can change it to 600. And now we should get the exact same result, and it is either the same or very, very close. And I'm going to leave it to the default, and I don't need to change that. And what I want to do, instead of injecting the temperature, okay, I want to use the temperature field as a flame field. So this is what the combustion model is looking for. And if I hit play now, we shouldn't see any temperature or anything, because the combustion model is turned off at the moment. So what I'm gonna do is I'm gonna go back to, or let's set it to 1 and see, just to confirm what I said. Yep, so we're not getting any temperature, we're not getting anything. And if I go, I don't like it, I'm gonna delete this. So if I go back to the, if I go to the flame tab and go under the temperature and say add temperature, and I'm gonna click on add, we should see the smoke go up. And now what's happening is we're getting the flame field injected into the temperature field. And it's because we set the value of the flame to 1. If I lower this to 0.1, we should see the exact same result as before, or very, very close. And the reason for that is because we're copying the flame into the temperature. Okay, but it's not exactly the same, but very, very close. So I'm gonna lower this to 0.1 and hit play. I don't want the smoke to rise a lot, and or actually I wanted it to rise quite a bit. Pardon me. So 0.5, and what I want to do is I want to lower the flame lifespan to 1, and I want to increase the cooling rate. I want the fire to die off very, very quickly, or the temperature to die off very, very quickly. But before I do that, I want to make the viewport or the display here a bit better. So I'm going to go under the multi-field, and we're going to set the same thing as the visualization node. So density, I don't need it here. I'm going to set it to 10. Okay, unfortunately we cannot use the viewport or the lighting here because it's a different context, but we can get the temperature to show up. So let's set this to 1 and plug in the temperature. I'm not going to use the black body, we'll talk about that later. And I'm going to change this to a clamped ramp and a black body, And I'm going to tweak the colors as well. Okay, and this one. I'm gonna also turn on the range and make sure it's the same value. So let's increase this to 100, and now we see the temperature field. I'm gonna increase this to 10, this to 10, maybe 25, and now we are seeing our temperature field in the viewport inside of DOPs. And what I like to do now, I like this, but I want it to decay very, very quickly. So instead of 0.5, I'm going to increase this to 8.8. So 80%, and that will, will decay the temperature and causes it to rise less and less. So we're going to go a bit higher, 0.9, and maybe lower the temperature amount to 0.25. Yeah, you can see here it's dying off, and I like it. So what I'm going to do next is I'm going to add some dissipation. I don't want the smoke to linger forever. I want the emitter to emit smoke and then dissipate very, very quickly. So I don't want the smoke to rise that high. And yeah, you can see now this is happening. But we're getting that clipping issue, and as I explained before, that is because the temperature or the settings are only accounting for, you see, reference flame, density, and flame. I'm going to add extra field temperature. And I'm also going to add it here. It's here. So if I hit play, we should see it not clip the temperature field and account for it. It still does. It's not the same. And the reason for it's clipping is because the temperature value is getting really low, and the temperature value is getting really low, and that threshold is not enough to keep the smoke accounting for that. So let's increase the padding a bit more to 0.5, and let's put it here as well just to make sure. Because if the value becomes really low, but we're multiplying it by 10, it's going to clip it regardless. So we have to be very careful. And you can see now it's working. So let's also decay the cooling rate a bit more. So 0.9. I'm gonna increase the buoyancy scale. I want the fire or the flame to go up very quickly. The temperature to go up very quickly, but then dies off very, very quickly as well. I don't want it to raise to this height. So let's do a bit more tweaking then. And let's try to lower the lifespan of the flame. Maybe that's having a big effect on this. Yep, it does. So this is what I'm looking for. 0.25 and 0.9 here. Cool, something like this. And I'm gonna lower the dissipation of the density to 0.1. I don't want it to die very, very quickly. It's too much, so 0.2 is good. Yep. So we have smoke, and then just fire keeps rising up to the top. And what I'm gonna do is I'm gonna go up, increase the resolution, and I wanna do a cache of this. So I'm gonna increase it to 0.3. Go up, I'm gonna copy all of this. And I'm gonna copy the compression nodes. And this. Also change this. And then the object name is not the same, I believe. Oh, it is the same. Okay. So we're gonna call this ring or live pyro. I'm gonna call this final. And we're gonna save 60 frames and we'll continue in the next video. Thank you guys for watching and see you in a bit. Bye bye. Hello everyone and welcome back. So this is, the sim is done. I'm gonna copy this, create a file node, read it in. I'm gonna use the old visualization node. And this is what we have. So if I hit play, this is our sim. And as you can see, it's actually quite fast because the files are not that big on disk. I'm getting some cool result. So I'm gonna lower the density emission, or let's try 25. Yeah, I'm gonna lower the density dissipation. I want to keep some of the smoke rising up a bit higher. So here I'm gonna set this to 0.1, and I'm going to turn on all these nodes, all these turbulences, all these microsolvers. Right now, all the details that we're getting is simply because of the noise in the temperature field and the noise in the density field. That's breaking up the emission. It's breaking up the simulation as well. So I'm gonna add post breakup. So this is the microsolver, and let's see. I'm gonna change this to 0.5. And let's do a quick sim here with these microsolvers turned on. And you can see we're getting more breakups now. We're getting more flames and everything. So let's tweak them a bit. And the wedge library is your guide for this. So if you want to understand any of the controls, you will find information about that. I'm gonna increase the turbulence to 1. I want to get it much more turbulent. And you can see it's very, very strong, especially in the beginning. So I'm going to lower that to 0.5. And I'm going to create a second one, gas turbulence. So if I have, what I do is if I have one at this value, swirl size of 1.5, I'm going to add the second one that is lower, 0.5 for example, and the swirl size is bigger. So we can add this. We can add this as in the forces. I'm going to set the scale to 0.25 and the swirl size to 3. Okay. And let's hit play. Okay. Let's increase the disturbance a bit more. Well, let's try 1. And let's also increase the shredding. Yep, I like it. Now the last thing I want to add is a tiny bit of expansion. I want the flame to be used, just a portion of it, not the entire flame. So maybe 0.8, and I'm gonna set it to 2 here so I can see how is it affecting the sim. You see it's expanding a lot. I don't want that, so I'm gonna just add a tiny bit, 0.1 maybe, and let's see how that looks like. Okay, I like it. Alright, that's it for the settings. The last node I want to add, which I always add, is the vortex confinement, and this simply helps improve the overall sim. And to chain multiple microsolvers, I'm gonna put a merge node and just plug them all here. I'm gonna set this to 1. Let's see how that looks like. So this is going to simply capture and enhance the velocity details. That's all. It's not gonna make any major difference to the sim, but if you increase it too much, you can actually start seeing weird effects from this, so we have to be careful. We're gonna go with the value of 1. I'm gonna lower this to 0.2, which is pretty high. It should be in the 500 range per axis, and I'm gonna call this high res tweak. and we're gonna save it to disk. I'm gonna save 90 frames. We'll continue in the next video. Thank you guys for watching, and see you in the next one. Bye bye. Hello everyone, and welcome back. So this is the result of a flipbook capture from OpenGL, Houdini OpenGL, and I used a 1024 resolution to make sure that I capture everything, and I'm pretty happy with the result. I really like how we're getting these nice wispy details, as well as the emission and fire and everything. I think it's working really well, and we're getting high resolution. It's super fast to sim, and that's how you get your first sim in Houdini. Alright, so this sim that we didn't inject velocity. Remember when we set up the volume source, we had density, temperature, and velocity, and we want to create some velocity so that the source has some force. Right now everything is coming from the micro solvers, as well as the temperature field, which causing it to rise. So let's do that. I'm gonna go back to the source here, and because this is a volume, it's going to be hard to compute a velocity field that matches the movement. So what I'm gonna do is I'm gonna copy this and plug it into the original geometry. Okay, so this is my geometry, and I'm going to fill it with points. So VDB from polygon, or we can use this one. So this is the volume. Okay, and I'm gonna scatter a lot of points in there, and I don't need any relaxation, just points. I'm gonna put 5,000 points, 8,000 points. Cool. And now if I plug them here, we get the deformation that we want, and then I'm gonna use a trail node. Trail node will be able to compute the velocity on these points. So compute velocity, and if we display it, we get this vector. Cool. What I want to do now is convert this into a volume. So we're going to use a rasterize volume rasterize node. Volume rasterize attribute. I always get confused. So the attribute that we want is V. The coverage we want, it's okay, we can create an attribute called density. So I'm going to put down a wrangle node, and I'm going to create f at density equal 1, and the attributes are density density and V, because we need the density for this thing to work. And then I'm going to lower the particle scale to 0.1, and if we middle click, we should see a density field and a velocity field. We don't have to sample the attribute, but it's good. It's better to have it so that we can rasterize it and use this coverage attribute. If we don't have it, then the result is going to be a bit off, but I mean, this is going to work fine as well, but to make it look proper in the viewport, it's better to have a density attribute. Now these two will not be 100% the same, you know, in terms of result, but because we're going to tweak the particle scale to give us the result that we want here. I'm going to lower this to 0.5, and now we have a density field and a velocity field, and all I care about is the V. I'm going to name it vel instead of actually no, we're going to keep it as V. It's fine. Yeah, it's easier this way, and I don't need the density field, so I'm going to blast it. And I only need the velocity field, and it's a vector field. See vector 3, and I'm gonna merge it with my result here. And to keep everything consistent, yeah, these two volumes, to keep everything consistent, we have to make sure that they are all VDBs. Okay, in some cases, if you use volume Houdini native volumes, you will have VDBs. You have volumes and VDBs. It's better to make sure that everything is of the same format. So in this case, it is. And let's go back to the sim pyro. I'm gonna lower the resolution to 0.6. We're gonna keep everything the same. and let's go to the source and see what we have. We already have this set up correctly, so it's looking up for a field called V and it's putting it into the target field vel, and this is what the Pyro solver will be using internally. It's called vel. The attribute name can be anything, but in this case, because of the volume rasterized node, the volume attribute rasterized nodes, it's called V. I'm going to use that as the default. So I'm going to scale this to 100, and we should see the smoke shooting out very, very fast. Okay, so 10 is good. But what's happening right now, it's the smoke is pushing in the way, in the direction of the object. I don't want that. I want to negate it in the opposite direction. So minus 10, so it leaves a trail behind it instead of pushing upward. And it's still very high, so I'm going to lower it to -1. I just want a little bit of kick in the beginning. Yeah, you can see how it's behaving in a nice way now. I think it's still strong. But we will keep it like that. And let's go back here, and I want to add a little bit of randomization to the velocity force. We can do that using a volume velocity node. So this is my volume, this is my V. I'm going to plug this node here and go to the curl, and I'm going to add curl. You can see it's changing the value. One way to visualize this that I like to use is to put down a scatter node and scatter points. Not on this one. I can scatter points here, and I don't need them to be organized. And then I use a volume trail node, wants points, and then a velocity field. And make sure it's using the V, and that's how the velocity field is going to look like now. If I disable this, you can see it's just a circular motion, and if I add the volume velocity node, we can break it up, and we have to make sure, yeah, it's adding. Cool. So yeah, it's adding. I was worried that it may be overriding, but it's adding. So we're gonna do it like that, and then it changes over time as well. So this velocity is gonna change, and that's the result we're gonna use instead. And I'm gonna go back to the resolution, increase the resolution to 0.03, and run another sim, call it with vel. And I want to do one more thing. I personally don't cache velocity. We don't need to cache velocity at the moment. We're going to talk about this later, but for the sake of practicing right now, we're only going to cache density and temperature and flame, and I'll explain why flame later. So the field is called flame, and it is invisible as well. I'm gonna save this to disk, and then I'll do a viewport capture like this one and continue in the next video. Thank you guys for watching, and see you in a bit. Bye bye. Hello everyone, and welcome back. I wanted to show a few more things about Houdini and doing viewports. So what I've done is, this is a 1024, and this is the sim ready with the velocity. And what I'm gonna do is right click on the flipbook with new settings, make sure the resolution, both of these are off, and then set the frame range to whatever I have to match the number of frames, and then hit capture. So it's going to use this resolution, and it will start doing the viewport capture and put it in an M-play. And this is one way of doing it. The other way is to use an OpenGL render, which is what the wedge setup uses. So the wedge setup sims and then runs a OpenGL render and saves the output to disk. In this example, we're just sending the capture to the M-play, and then we can export an MOV out of here, or a movie file. So this is the result with the velocity. You can see the smoke is pushing, and it's moving, and it has noise and everything. And this is basically covers the entire workflow that we need to get used to. And to save an MP4 or a movie out of MPlay, you need to install something called FFmpeg. So this is a library that you, or a software that you install, is free. And what you can do is you can go to FFmpeg and export sequence or export movie, whatever, and then save this to disk. I'm gonna set it to MPEG 4 video high quality, and you have to make sure that these numbers are pair. You cannot have, you know, a 3 or 11. The number needs to be able to needs to be dividable by 2. So I'm gonna set it to that and save, and I have my files. So this is with no val, and this is with val on the site. So I saved both of them to disk. Cool. Thank you guys for watching, and see you in the next video. Bye bye. Hello everyone, and welcome back. In this video, I wanted to talk about hardwares and the configuration I have currently, and what we've used for this workshop is the AMD Threadripper 3960X with 24 cores. I don't remember the clock, but I think it's 4 gigahertz. And the one I'm currently using to record these videos is the 3970, 32 cores at 4 gigahertz, I believe, as well. So this is what we've used. Anything, or when it comes to CPU, anything that you have access to should be enough to use to create sims, as long as you have enough memory. The minimum that I recommend, 32 gigabytes. It's not going to allow you to create high-res sims, but it should be able to allow you to practice everything you need. And by that, I mean you can create every single assignment and sim it, but you won't be able to push the resolution as high as we can, because we have more memory, as simple as that. And it should not prevent you from creating nice sims, nice motion. You just won't be able to increase the resolution to something really, really high. And when I say really, really high, I mean something with, you know, 1000 in one axis, 1000 in close to 1000 in another axis, and 600 or something like that. So this would be super high res. Mid res is when each axis is between 400 to 600. Or let's say this is high res. Okay, it's high res. Mid res is the 300 range. This is mid res. And then low res would be anything less than 300, like 250 by 250 by 250. And you should not feel limited or anything by using whatever resolution you can achieve. The techniques are the same, are still the same. The workflow is still the same. The practice is still the same. The only the other thing that you have to account for is when you create a high-res sim, regardless of, you know, when you create a sim, expect 100 megabytes per frame. Okay, so if you're gonna save 200 frames, that's 2 gigabytes. Just account for this ratio, 100 megabytes per frame minimum. It can go up to 600 if we start adding a lot of fields in the velocity field. Now, you don't need these CPUs. You don't have to have these CPUs. A simple explanation is the more cores you have at a higher frequency, the better. But there is a threshold where it starts flattening. So for example, this 32 cores, 2 cores at 4 gigahertz. Okay, I'm gonna do the math. So 32 multiplied by 4, 128 gigahertz. If I get a 64 cores at 3.5 gigahertz, it's almost 2 times more frequency, and it's 2 times more cores. So the sim will be 4 hours, let's say here. It's not going to be 2 hours here. It will be maybe 3 hours and 20 minutes. Okay, so it starts tapering off. The same thing between these two, the 24 cores and 24 cores multiplied by 4.2 gigahertz. Okay, let's so 24 multiplied by 24 multiplied by 4.2, it's 100 gigahertz. The sim time is going to be 4 hours and 30 minutes. It's not going to be majorly different. Okay, and these are just example. More cores does not mean faster sims. If you have access to 4-core CPU with dual threads, even like an old i7 from 10 years ago, and it has 4 to 5 gigahertz, you are able to get a lot of sims done. Okay, in fact, a lot of the old work that we did was using 6 to 8 cores i7 with 3 to 4.5 gigahertz per core. Okay, so you can get a lot of stuff done with and with 32 gigabytes memory. Having 64 is a really good range. 64 gigabytes of memory is great. Another thing to factor in is another thing to factor in, forgot, I lost my train of thought. Yes, so another thing to factor in is the operating system, whether you're using Windows or Linux. On average, there is 20% less memory usage on Linux. So if you have 64 or 30 gigabytes, you will get way more usage out of it compared to Windows, because Windows has a lot of extra things that it needs to carry. Linux, it can run on 800 megabytes. That's it. Everything else will be used for Houdini. The next hurdle is to use do viewport capture. And as you guys saw, I've hit the 2.5 gigabytes on Houdini very quickly. I'm gonna open NVIDIA SMI again. This is a command line I use to check. So right now I'm at 6 and Houdini is using 2.5. Okay, you don't have to display volumes at high resolution. You can just rely on Mantra or on the render to see the final result, and you can do a still frame. Just put the volume, hit render, or use a pre-build in from the shelf, and you should be able to get a viewport capture. 2 gigabytes of memory is a bit limiting. 4 gigabytes will be good. 4 gigabytes you can get some stuff. So you don't need a 2080 Ti. You don't need a 2080 or anything. Even those like 960, 970, and the old cards, even 880, as long as it has enough memory, it should work perfectly fine. When it comes to more professional work, if you're going to be doing serious work, then having a dual Xeon or an AMD Threadripper would be the way to go, but it is not required for experimenting and learning everything about Houdini. Okay, I think that's pretty much it for the hardware. Just I'll share more in the assignment video about the guidance and how I want you guys to work and what needs to be done. Thank you for watching, and see you in the next video. Bye bye. Hello everyone, and welcome back. So we've covered a lot of things this week. We've gone through the workshop breakdown. We've talked about what we're gonna do. We talked about the wedging. We showed how to build a simple setup in Houdini, how to get everything going. This may feel easy and accessible to everyone, and we wanted it to be that way. If you have prior experience to Houdini, please get used to using the new workflow and make sure you know where everything is. Also, the wedge that we're going to be providing for all the settings that we've done, all the wedges, please take a look at all of them and see how changing those values affect the result. What I want you guys to get used to is, or get to, is to build a visual memory of what tweak or what settings you change and how will that affect the result. I don't want these guides to be side by side all the time. You need to watch them and try to build like a library, a visual library, so that when you change values, you don't have to always go back to this or wait. You can just go straight in. You know how this will work and how this will affect the sim. You just start with a really good values, and that will save you a lot of time experimenting. The other thing is, everything here is new. So even if you have prior experience, I want you to go through this workflow and do some sims, save them to disk, iterate, increase the resolution, set up the wedge scene. If you want, you can use the wedge setup, do all these things like the ring or whatever source you're going to use, and plug them in the wedging system, and then try wedging some settings. For example, I want to wedge the velocity amplitude, I want to wedge the temperature strength, I want to wedge the resolution, I want to wedge whatever I want. You can do those things and get comfortable with the workflow. The wedging system we're not going to be using every week, at least on our side, on the instructor side, because we wanted to get things done very, very quickly. So we just focus on creating the effects. But this platform should be used for testing or for doing any R&D that you want to present or compare. So everything we're going to be doing, we recommend using the wedge setup and plugging everything in there, so you have it at least if you want to compare. The other thing, if you haven't done sims before, if you don't know your hardware limitation, if you don't know what doing a high-res sim is, please start doing that. I want you to create sims and start hammering the hardware that you have as much as you can. Okay, create a sim and let it run for 2 hours, and then look at the preview, do a viewport capture, save it to disk, run another one, let it run overnight, and then come back the next day and see how well the machine did. Try to reach the limit of what you're capable of, so that you know later what kind of settings you can go for. You know what the resolution, the maximum resolution, how you can get, how many voxels you can fit in the GPU, and whether you can use all of this or not, and just tweak based on that. You don't have to do high-res sims if the hardware you have cannot do that. Just get comfortable with the environment, because we need to be working and creating sims, even if they're not as high as they can be. And I think that's pretty much it for this week. I want you guys to digest all of this as much as possible, work on creating simple sim, and the result does not matter. I don't care too much about how it looks or how awesome the sim is or how high res the sim is. The goal is for you guys to get comfortable with the working environment you have and with the Houdini and the tool sets available. One last thing I wanted to add is we cached the flame field, and I just wanted to show how different it looks compared to the temperature field. So I'm gonna set the density to 0, and this is the temperature field. And I'm gonna go in this node and change everything that says temperature to flame. Okay, so I'm gonna set this to 0, and now I have the flame data. And you can see it's much more narrow, it's much more connected to the source, and it does not behave like the temperature field in any way. Okay, so that's something we have to be aware of. We can use this later for doing some advanced shading techniques if we want to use it in any way we want. We can use it to process things in SOPs if we want to use it to emit particles, or for whatever reason that data is available and it's not the same as the temperature field. So that's what I wanted to show here. And I think that's it for this week. Best of luck with everything, and please let me know if you have any questions, and talk to you soon. Bye bye.
Okay, so the art of explosions. So I just want to show you a lot of different explosions, and I'm going to talk about what makes them look good and what makes an explosion look good versus a bad CG explosion. And then we're going to be also be looking at some real life references. So this is a breakdown from the Avengers that ILM did, and you can see obviously the explosions are CG, but what makes this explosion so good? And one of the big things is it has different color variation, which is something that we were doing as well. So you can see there's color variation. You have black and you have some white smoke, and then you have some gray in betweens, and that's really important to break off to break to make something look a bit more realistic, because most of the explosions you see out there that are CG, they're just gray, and that really breaks it. The second thing is you can see how their emission starts. They don't start the emission immediately. First you get just the smoke coming up, and then it kind of the flames come after the smoke. So it's almost like you would pour gasoline and then you light it on fire, and that makes it essentially you stage your explosion in different stages, in different steps. So not everything just happens at the same time, but you actually have stages. So you have stage 1 where you just have the smoke, stage 2 when it gets lit on fire, and then they also do multiple emissions of the explosion. So you can stage it up, and that comes then down to art directing. Because just imagine if this explosion was just one big puff and everything goes up, it's not very pleasing to look at. Also, one thing that people say with explosions is that you have to destroy the mushroom. Like the mushroom shape that it makes it look super CG, if you have mushrooms. And that is actually not that true. Like every explosion has mushrooms. That's the whole thing. You're going to get mushrooms with explosions, even with real ones. There's no avoiding that. It's just what's going to make an explosion look good is actually breaking those mushrooms into more mushrooms. So let's say with this is all one big mushrooms, but look at it. It has multiple shapes to it. That's what you have to break, not the actual mushroom. You cannot break, this might be even better if it had more shapes like this. But this is the thing you have to break. You see, like you get multiple shapes, and that's the thing when people usually refer to when they say that you have to break the mushroom shapes. There's no other way of actually making an explosion without having these mushroomy shapes going up and billowing up, because that's what the real explosion does. And so I think we can all agree this looks pretty amazing. And you can see just based on the breakdown that they have, I'm going to show you that what we're going to do in our workshop is actually the same thing. So look at this pass. If I go to Houdini quickly and I start this render, you will see that, and I hope Mantra is a bit faster today than usual. There we go. So if we look at this pass, which is this is the emission pass. So you have the smoke, you have your emission, and then you have the emission multiplied by the density. And this is what gives you the really cool, crispy shapes. This is one of the tricks how to get this. And so you see we're getting this, which is, I think it's really close to what we just saw with Avengers, which is just crazy that we're able to do these kind of explosions now, that we can actually match the level that they have on this multi-million budget movies. So this is the combined density multiplied with emission. But if we just go to the emission part, you can see this is looking exactly the same as in Avengers. So the way we learned all of these techniques was actually just watching breakdowns and seeing how they do it on the big movies. And that's how we learn as well, by just looking at breakdowns and trying to figure out how to do all of these techniques. But you can see when you multiply the emission with the density, and I can showcase just the density. This is how the density map looks like. And then we use this map. Just imagine like an alpha map, and then you multiply this with the emission, and you get the nice details that we all want. think this looks pretty good. Anyway, let me go back to Premiere. So I just wanted to go through a bunch of different things. This is the same kind of technique, very similar, that we used in one of our other promos that we did. But this one is actually using a bit of that inverted shading technique that maybe some of you guys, maybe you heard of it, the inverted pyro shader. And you can see it here on this Destiny cinematic as well. Now, I'm going to be this is my personal opinion. I'm going to be going through these cinematics and just telling you guys what I think works and what doesn't. And this is in no means me like talking badly about the work that the artist did, because I'm going to be showcasing some of my work as well that I think doesn't look the best. But this is just all for academic purposes. We're just, I'm just showing you guys what works and what doesn't, and the different ways that people render explosions, and why this way that we're going to be showcasing in our workshop is, I think, the best way that you can do explosions right now. But you can see the inverted shader here happening. And also it's a bit blown out. And it just doesn't look right. The reason why we were doing the inverted shader is because that was the way that we got these black crispy details. If we inverted the shader, not inverted it, you just remap the emission, so it kind of gives you that flamey look, and I'm going to show you how that looks. So this is a cinematic that I worked on, and this is my explosion. And you can see I was doing the same thing. We were going for that gassy explosion, fiery gassy explosion look, and there's a bunch of things going wrong here that it should be more bright. Because if it's a really, we wanted to expose for the flames in this case, but I think they should be brighter. But you can see here I was doing the inverted shader technique as well. And the reference that we had for that was, it's not that far off. So this is a real life flamey explosion, almost like a flamethrower. Actually, there's a flamethrower. And this is the result that you have. And that's kind of what we were going for with that reference, with that explosion. Let me go back to it. And in some cases, we actually succeeded in making it look kind of similar. But I'm not the biggest fan of this. When I worked on this, I still didn't exactly know how to make details like this. So the inverted kind of shader technique was the only way to do it. The thing that I like about this explosion is it has multiple stages. And that's what I was telling you guys when I was talking about art directing explosions. So you have this, and then you have the really intense burst of flames coming out of the barrel because he just shot a flaming arrow to it. And that creates a shape, and then that shape almost disappears. It implodes and then it explodes. And we have this one first big explosion happening, and then a second one. And you can see there's one big one, and then the second one happens, and it creates these shapes and the ground, the dust wave. It has multiple stages, and you have to think about explosions like that, so you have to think about how to make it more impactful than it actually is. This is another good example about that I think they were kind of doing the same thing that we are, where they were multiplying the emission with the density, and it just looks amazing. And they were doing it almost looks they are changing the color in the smoke. But the reason why this works so well is actually there's a different reason, and that reason is the Fibonacci sequence. And this is something that blew my mind when I first heard about it. And it's actually something you can apply to everything, not just explosions and not just effects, but you can apply this to music. You can apply this to your art, anything really. And the Fibonacci sequence is something that you can also call the power ramp. So if you have a ramp like this, this is kind of the power ramp. So you want essentially you want a lot of small pieces and then not a lot of big pieces, and then medium amount of medium pieces. I know it makes it's very intuitive, but if you look at this tree, you have one big trunk like here, and then you have 21 small pieces. And this gives you a perfect ratio between small, medium to big pieces. And see here, this is that scale actually. You see how many small emissions you have with the sparks and the trails, and then you have one big explosion. But even that big explosion is separated into multiple shapes. And that's what you have to look into. See, this is a medium-sized shape. This is a big shape, medium, medium, medium. Obviously, there's one big shape doing everything, but then you have a lot of small ones happening here. And this is kind of the Fibonacci sequence in play here. So you have, 50 of these, you have 10 of the medium ones, and then you have 2 of the bigger shapes happening here. And this is perfectly demonstrated in Star Wars. Because with Star Wars, you see this, you see how many sparks they add? So they really play on that concept where with a lot of small details and obviously destruction and RBD, you create a big sense of scale, because the more of the small things you have and sparks and RBD and all of these elements that fill out the explosion, the bigger the explosion is going to feel, and it's going to make it look I don't know how to call it, more meaty, like and this is a good example as well. And here you can actually see all the small trails that are happening, and then you have again, this is really important. That's why I'm repeating this. You have shapes. That's how I see explosions. All I see is these shapes, and then one big shape, and then a lot of small shapes. This is all I see. I just see shapes, and that's how you should look in explosions. And this is where you start art directing, and you can see they are doing the same thing. They're multiplying. They have the emission paths. They're multiplying it with the density, and that's how they get the nice and crispy explosions. And I just love watching it. I mean, look at this. Oh my God. Oof, so good. Here, another example of how many small details they added. And that's really important. The small details are sometimes more important than the big ones. Just amazing. I think this is one of my favorite explosions ever made. Look at how many small. I'm not sure how well it shows on the stream. But look, you can check this out. I think Last Jedi bombing. I think if you go the Last Jedi ILM breakdown, you're going to be able to see all of this in HD. But just amazing stuff. Another good example from King Kong. I think this movie is super underrated in terms of effects. What they were doing with this movie, like visually, it's so stunning. Just amazing stuff. Like, look at how much detail they were getting in the fire simulation. This is something this is actually a good topic maybe for the next webinar. We might do a flamethrower, and I can show you guys how to get all of these details in the flame as well, because the flamethrower is just a bit different than doing like a classic explosion. This is not related to explosions, but I think it just looks so cool. I think this movie has one of the best effects ever. It's in terms of water and fur and what they were doing with like scale in general. It's just so good. But there's an explosion coming as well. That's why I'm showing you guys this. There's going to be an explosion. So this one, look at this. This looks so full, even though it doesn't make any sense. So he just had, I think, a couple of grenades on him, and this exploded in the most brutal way. How did this happen here? Like, he had the grenade. I guess maybe he dropped it from his hand, but this is just huge for the grenade that he had. But it's so good. Look at the small details they added. So this is what I'm saying. This looks so huge because it has so many small details. And this is something I wanted to add to our explosions as well. So when we were doing these guys, I was adding a lot of the debris, but it's just not visible. You can see it here. There's I should have added even more debris for sure. But you see how many sparks I added as well, just to emphasize the scale. And then obviously I added the environment as well to showcase this. And I just remembered something. Completely forgot about this. So we're gonna give a 10% discount to everybody. I mean, to the first 30, maybe more people, but we're gonna do it with the first 30 people. And I don't know if Caleb already, because I'm not monitoring the chat, I don't know if he already showed you guys or sent the coupon, but essentially you guys are gonna get a coupon. I'm not sure, maybe at the end of the stream or maybe now. And that coupon is gonna have 10% discount on all of our workshops. So yeah, I just remembered that. I'm sorry, Caleb. I'm the worst at this, but this is how it is. So back to this explosion. It just looks amazing, and it's so beefy. It's just so good the way it explodes. It has so many details, so many small shapes that it makes it look amazing and huge. This is a bit old, I guess, but it doesn't matter because this is art directing. This is going to be all art directing, and I'm going to tell you why in a second here. So again, these explosions, if you look at the shader, in some cases, it almost looks like that just basic pyro shader that we want to get away from. Like, nobody really likes the basic pyro shader. That's why they, with Houdini 18.5, they created the scatter shader, and you can now combine it with the fire pass and all of that. And in general, this, like, when you on a still frame, this doesn't look the best. But why this works is because of the animation. The animation of this explosion is amazing. How fast it explodes, how many small elements it has. You see the sparks and everything, the debris, how the debris covers up the explosion. You see the shapes it creates, the spiky shapes, and the ratio. And the ratio comes back to the Fibonacci sequence. Like, this is a perfect example of the Fibonacci sequence again. And they were breaking the shapes quite well again. You see, it's not just one plume, it's not just one mushroom, it's multiple mushrooms. And that's what I'm talking about when I'm saying art direction. So yeah, when I'm talking about art directing the explosions, you see this one, like, I'm not the biggest fan of this shader, to be honest. It looks super stylized and it doesn't fit this cinematic. This cinematic is supposed to be super realistic, the way they were portraying it, and this shader looks almost cartoony. But look how fast it explodes, and that's why it gives it. It still feels like a really massive blast, and it still works. It portrays the emotion, what they were trying to show with that effect, and that was that he got hit really hard, but he still keeps walking forward. So it's not all about the shading techniques. It's, in a lot of cases, it's about how you know how to art direct your explosion. So it creates the emotion and it moves the piece forward. And when I say the piece, I mean the cinematic or like whatever trailer or movie that you're doing. So this is a cinematic from Titanfall. And this almost had the right details, but still not quite. And I believe this was done with Fume Effects. And it did have the, kind of the crispy shapes, but it's still not the right kind of crispiness that that they had here in Star Wars, right? It's not the same crispiness, and it's not the same crispiness that we have in our explosions. Maybe not this like this crispiness. And I think they were also doing the inverted shader in that one. But they also had some geolights. So you can just use the volume and convert it into a VDB and turn that into a geolight, and that will give you this inside illumination of the explosion. But that is really slow to render. And with the new scatter techniques, you actually don't have to do it. This is another example from ILM, and this is back in the day where they also didn't have that scattering technique. Like they still didn't perfect the crispiness that they have right now. That's why I wanted to show you guys. But it's still, the explosion looks good. It just doesn't have the right shader yet applied, like here. So this is a very similar shot with the explosion, right? With the ship exploding. But what Megalis did, they have this nailed down. They have the look, the scatter look with the crispiness, and I think it looks way better than what they did on the battleship. Obviously, it's an older movie. I'm not saying it's bad. I'm just comparing the two shots, and this one to me looks way better. And again, the Fibonacci sequence is amazing. This is one of my favorite explosions, and we obviously borrowed from it in our nuke explosion that we did. And this just goes to show, like when they did these passes, you can see this explosion doesn't have a lot of details. It actually looks super low res, but with the comp and the secondary elements and all the passes, all the glow passes, it looks amazing. And because it happens so fast, and the speed of it, again, art direction, it just looks amazing. It looks like the biggest thing ever. But when you break it down into layers, it's not that high detail. So don't be concerned with voxel count. A lot of people, they think the more voxels you have, the better your explosion is going to look like, but that's usually not exactly the case. You can create something that looks super high detailed and amazing with a low voxel count. So this is another example that we were trying to imitate with our workshop, this kind of spiky explosions that happen. And I have a perfect real life reference for this as well that I'm going to show you in a second. But here you can actually see how they did it. And I really like watching breakdowns like this. I'm pretty sure they didn't use these particle sims for the actual emission. I think this is something the animators have to showcase where the effect is going to be. And then they create different emissions. Actually, I think they have the same emissions that we are going to show in our workshop. I mean, to be honest, we came really close to this result, and that was kind of the goal. Like if you look at this, that's pretty much, it's so fast. But yeah, that's pretty much almost like a one-to-one reference to the Avengers. It's another example from Star Wars. I mean, look at this. Amazing. Just so good. I think I saw this clip like a million times. But again, like maybe it's not here, but yeah, just like this one, the multiple stages, the way it explodes. So it explodes once. It explodes once, and then it has another internal explosion happening, like here, and then another big one. So you can see the stages. It has 3 stages. That's the blocking of explosions. That's going to make it look more interesting, bigger, and yeah, that's what you should be looking for. And then these explosions are the ones that we're going to give you the free HIP files at the end. So if you stick to the end, we're going to be giving free HIP files to these setups, and these are done with Houdini 18.5. So we just tweaked them a bit to make, you know, this carpet bombing happening and having all the trails with you know, sparks and lights at the end. So I think it's a cool example. This is a different kind of explosion. I'm not sure who did this. I'm not sure if it's ILM, but it's on Avengers. And it's something that Saber, the CEO of Rebelway, did as well. So we did this one, which is very similar to the other explosion in Avengers. It's a completely different type of shading. And it's very interesting to see as well. And it doesn't use this concept, the emission multiplied by density. It's a different concept that it uses. And yeah, it's very interesting to see. And I'm pretty sure he's going to be showing some of this in the workshop as well. And this is another example of that shading technique. And this is from our cinematic as well that we did. All right, so these are, I think, all the CG explosions that I had. And yeah, this is the thing I forgot earlier, but yeah, the first 30 people will get a 10% discount, and the discount will expire in 5 hours, maybe a bit more. I'm not sure, but yeah, it has a time block on it. So if you are undecisive, if you want to join a workshop or not, I think now it's the time to do it. So looking at cinematics and movies is one thing, and it's good because they had concept art, and they had you know, in a lot of cases they were looking at real references as well. So if you do explosions, and just like as an FX artist, you have to look at real life references. And Action VFX, actually, they have amazing detailed explosions. If you go to their website, you can just see they actually shot these on camera. So these are real explosions that they have, and real like smoke bursts. And you can just see how much detail this has, and how like it almost starts raining down at the end. And this is something I wouldn't think of if I didn't see this reference, but it makes it look so satisfying. And because it's mostly a smoke explosion like this, it doesn't have a lot of temperature, so it actually goes down super fast. Like it's hot in the beginning, but then it goes down. You see, like it's almost like buoyancy is -1. So this is a good place to get references. This is another good reference that I was showing you before. And in some cases, it just looks unrealistic almost, because you don't see explosions like this from this perspective. But see how the fire just climbs up and catches the fuel on fire. And this is just so interesting to me to see. And then look at all the small, you see all the small things at the end, like the fuzziness of the droplets happening. Like this is something, if you want to create something that looks super realistic like this, like you would have to take that into account. Yeah, just some nuclear explosions. I think this one is super interesting. You see the ring that it creates? I'm not sure what exactly that gas is and how it creates it, but it just looks so unrealistic, and you would never think of it. Because if you would do this in an explosion, it would almost look fake, but it's actually like this happens in real life with explosions. And it's something that we actually did when I was doing the nuclear explosion. If you look closely, you see this black shell that's happening. So that was the gas leaving the explosion. And that's why this explosion feels like it has multiple stages, because it actually has. It has the first stage, it explodes, expands super fast, and then all the rings appear. And it feels like it has multiple stages. And like I said, it's because it has. And also, I think this is pretty cool, like how the ring shows at the top, and the setup is actually procedural, so the rings are actually showing based on the height of the explosion. So yeah, we're going to show how to do this in the workshop. Hey guys, we're almost at the end, and then we go to Houdini. Another really cool reference, and this is the one, the spikiness that I was telling you about, the spiky reference. And this is probably what the Avengers guys were also looking at. So you see the difference in color variation. You have some ground that is actually more brownish dark, and then you have white, and then you have more grayish dark smoke happening. And this is based on what ground it hit. And the important thing here is you can see how they don't billow. These explosions, they don't billow that much because they don't have a lot of temperature. They're mostly done, and they don't have much gas in it or burn. They're mostly done with just smoke, and they don't billow up. They actually see how straight these lines are. They're so pointy, and they just kind of break apart a bit. They never become a full mushroom shape. And I think this is something we achieved quite well as well with this one. If you look at here, at this part, see, it just goes up. It never actually breaks. And this is something that is difficult to do, and I'm going to show you how to do it. And then you have some of them that actually billow out like this. And this is something, and this goes back to when I was saying that some people say you have to, CG explosions, they create mushroom shapes. It's not true. Like, this all creates a mushroom shape at the end. That's just how it is. That's how the smoke expands, and in real life as well. But again, look at the difference in color as well here. So that's quite important. And then another one that I think was just so good. In terms of, you see how much detail there is with the chunks of the ship happening? It's actually quite important, coming back to the Fibonacci sequence, having all of those shapes, and they fly way more up in the sky because they're smaller, and they go way off the screen, and that's also important when you're art directing. Okay, and the last one. This one was interesting, the way. So this one actually looks like that explosion from Titanfall that I was showing you before. So this really goes to show how many different explosions are going to create different type of emission. So not the scatter shader doesn't actually apply. I mean, you can do this with the scatter shader, but I'm just saying not every explosion has the same look. So you have to take that into account when you're creating explosions, that not all of them actually have the same look. Okay, guys, I think this is it for the references part and the kind of the artistic part. Did you guys enjoy that part? Because I really like talking about stuff like this and just looking and going through the references. I mean, do you guys like stuff like that? Because if you do, in the next webinar, we can do more of these and just showcase more references and breakdowns. Okay, because I think this is the most fun. Just gathering references. You know, when you're working in a studio and they give you a shot to do, and then you spend like 3 days just looking at references and gathering data. It feels like you're a scientist gathering data and trying to evaluate how to do this effect for real before you, and then you start calculating the forces and how much fuel you have to inject and how big is the space and everything. I just find that super fascinating. But yeah, let's go to Houdini. I think we have enough of enough of the references for now.
Hello guys and welcome back. In this video we're going to learn about LUTs and how they work and what's the advantage of having a LUT in general and how to use them in Houdini and how to set up the Asus workflow. Now I have a render here, I have a scene here with a skylight. I only have a sky dome with an HDR, and I have a sunlight, and I just turned it off, so it's just the skylight right now. And I'm going to increase, try to tweak it so that we see a little bit more information from this HDR. Okay, so I've increased it to 40, and let's see what we get. And look, you can see now we're getting a lot more information from the HDR, but everything is blown out, everything is super white. And look at how these fall-offs are. We're getting very clamped images, and the result, if this was correct, the illumination result from this should be much higher. We should be getting a lot more information back, a lot more indirect illumination from that. But we're not getting this. And if we tune it down, you can see as soon as we hit white, it becomes white. It becomes super washed out. And this is a big problem. Let's introduce the sunlight. It's probably too high, so let's set it to 6. Now I'm trying to add this a sunlight back to try to get some more information into the scene. But so far, everything is getting clamped at 1. We are not able to see anything above, which is basically what everyone is doing when they use the render by default or they don't have a LUT workflow. And the main reason movies look much more realistic by default is because they have these LUTs workflow. They have a LUT for every movie, and every render you do generally render in the same color space as the movie was shot. So for example, there is a very common format they use in cinema, it's the S-Log, and the actual camera capture, the image range goes from 0 to 54, and when you look at the raw image, it's not interesting. It's super flat. There is no contrast. There is nothing. But once you apply the LUT to it, it looks way more better than anything you've probably seen. And that's why they look much more realistic, either the render or the camera itself, because they capture a lot more information than just a range of 0 to 1. They're not limited to that. And with this sRGB workflow, we're rendering in linear space and then looking at the result using a 2.2 gamma, but we're limited to white. This is as high as we can get. That's it. If we surpass this level, we're not going to get anything interesting. And this is not enough for us. This range is very limiting. It doesn't help with the physically based render, because if I expose this, if we were to shoot an environment, a real photo, if this area looks like this environment will look much brighter because of that intensity, but it does not here. So there is something wrong. There is something broken, and this, what we're going to be doing is what will take your render to the next level. There is nothing else. If this doesn't make your render better, then there is something else that you need to revisit. And by just having this LUT workflow, once you get used to it, there is no way you're going to render without it at all. Your render will look, once you get used to it, your render looks much better by default. And everything you saw in the workshop, every single image here. Let me pull up the link. Every one of these guys is raw render. Every one of them, including this, which in this kind of stuff is basically impossible to get if you were in a normal workflow. All these images are done, are raw renders. This one too. Everything you see here, There is no compositing involved at all. And it was done using the Asus workflow, which is the LUT. Now let me continue tweaking this. Let's go back. I'm gonna snapshot this. Actually, I'm not gonna snapshot. I'm gonna take a picture, because if we take a snapshot, it's taking into account the LUT. So I'm gonna call this no LUT. And I'm going to turn on the LUT and retweak this. And I'm going, we can load a LUT using this. So load the LUT, and this is what we're going to be using. And I will explain where these came from and how to install the workflow. And you can see by just doing that, something changed already. See, this is the original one, and this is with the LUT applied. But now we don't need this stupid 2.2 gamma correction. We don't want that. We're going to set this back to 1. And this is what the render looks like with the LUT. Now look at how much information we have. This is without the LUT. Look at how much information we're getting clamped in there. And then once I turn on the LUT, look at how nice these shadows are and these highlights. And this is much more realistic. Now look at the difference, the illumination coming from this wall. It feels much more realistic, because now if I look at this value, see, it's 1. Let's gain this image. Okay, let's go to, it's not very high. So let me change few values in the lights. I'm gonna leave these guys here. I'm gonna load this for LUT, both of them. And for LUT. And let's hit render again. Cool. So these lights are much brighter, and let me tune them down. So let me set this to 100 and 40. And you will notice quickly that we need to, once you start using this workflow, you will see that you need to increase the luminance much higher. Now I'm just using the sky dome, and let's increase this to a stronger value. You can see now we have much better information here. Let me crop it to this region. Nice. Now look at how awesome this transition is. We're not getting any clamps anymore, and look at the value, it's 80. And look at the indirect bounce from this, it's much more realistic. And let's go higher. Let's go 80. Now this is a lot more higher, and we're still not getting white yet. Look at the values. At 24 here, and we have 24 here, and we're seeing information. Look at this. We're seeing information there, and this is basically the key to getting realistic renders. We need to render between 0 to 100, let's say 0 to 20 and above. And I set this to 200, probably too high. And let's introduce the sun back. I want to introduce this guy back in. And look at this. Look at how awesome the highlights are. We're not clamping anymore. Oh man, I can't believe the sRGB workflow. Look at this. Now with this, we're gonna get a lot more information in the highlights, because it's not gonna clamp. It's gonna look way more realistic. We can push the values, and we're gonna get much nicer fall-offs in general. And this is not color correction. This is very different than color correction. You will not get this if you take the image in sRGB and try to do it, try to color correct it. You will never get the same information. We're rendering in a different space that is not sRGB right now, and it's the Asus workflow. And what this Asus attempt is, there is many different LUTs. You can find them online. The Asus workflow is the attempt to create a standardized color space where everything will look the same using the same monitor. And they have different simulators for different camera. And the default one, Asus CG, is great already. You don't have to do any further tweaking. You can see we're getting also a lot more contrast in the shadows. Okay, in the mid-tone, in the black tone, we're getting nicer saturation. It looks much nicer here. And now the colors will have to be tweaked accordingly, because there is also a shift where the blue will not look exactly the same. The blue that you will see here will not be exactly the same. So you have to tweak the values to give you what you want in the viewer. And let me turn this off again, and let's take a look. And this is without the LUT, and this is how it would look like if we were using sRGB. Let me gain it down, and this is these are the value. Let me set this to 2.2. This is the result. Okay, and you can see how flat it is. Actually, let me capture this. And let me open the image. Okay, so this is the capture. And let's put back the LUT. And let's set this to 1. And look at the difference. And there is nothing, I cannot stress enough how important this is. And now let me show you a cleaner version with just high-res settings. And this is the raw image. You can see here how nice these glows are. You're getting a lot of interesting illumination. It feels much more realistic because the light is behaving much more, it's behaving in a more realistic manner, because the value that we're seeing now is actually what's being used in the render. And we're gonna get a lot more highlights. You can see there's just tons of information, and this is one quick example. And let me put them side by side. This is the sRGB and this is the LUT workflow. Okay, now in the next video we're going to look at how to install the Asus workflow. I was using it through the LUT here, but there is actually a open OCIO profile, which if I turn on, it gives me this Asus workflow, and you can view the image under different format. I'm still not sure what this is for, but you can simulate different cameras and different color spaces. I use the sRGB, which so far gives me the best result, and you can look at the raw image as well if you'd like to, and see now how we're rendering between 0 to 20 or something like that, and we're able to see it nicely. So we can squeeze way more information out of the render. Actually, let me do one last test. I'm going to increase this to 600. I want to see the cap. So we're still seeing there is a little bit of fall off there, and see the values. And let me gain it down just a bit. See, we can see a lot more information, and this is this is what you need to use. This is the secret to photorealistic render. Even if you're not, I mean, I didn't do anything with this render. It's just a skylight and a sun, and I turned off GI basically, and I have the some water surface here to capture more highlights and more reflection. There's no secret to it. I hope this makes sense. I'm sure once you guys get used to it, you will start to understand what's happening. I'll try to find some more resources about it, but it's basically the way to go. Thank you guys for watching, and see you in the next video. Bye. Hello guys, and welcome back. So in this video I wanted to talk about the Asus workflow and the OpenColor.io pipeline. So if you go under the github.com/imageworks, this is a Sony open source project where they are hoping to create a unified color correction pipeline and for VFX and basically any CG related rendering. So if you go under sorry, not OpenColor.io, OpenColor.io-config, and under here you will see that there is this Asus workflow, and the latest version is 1.0.3, and this is the one we need. Now you can clone and download the whole package, and we'll include everything. And then all you have to do is extract these folders. So in this case, I've extracted them here. This is the package, and then once you extract it, you'll see it has all these folders, which is basically this, except I deleted these guys. So the one we're interested in is the 1.0.3, and inside this folder there is a config.ocio file, and this is an amazing thing for VFX in general. This this config file defines a variety of things that solves a lot of issues, and by just exporting one environment variable, all the other packages, mplay, Houdini, Arnold, I'm not so sure how much Mantra has this, I don't think they do, but mplay supports it, RenderView supports it, Arnold supports it, and then Nuke supports it, and Natron and various other packages supports it as well. So all you have to do is copy the path to this file, not the path where it lives, and then export an environment variable called OCIO that points to that file. And you're done. Now once you do that and restart Houdini, under the render view you should see this Asus workflow. You should see this option here. And the default is fine. We're going to be primarily using this. We're not going to change anything. And then the other thing that you will notice is when you open mplay with Houdini 16, the latest version, not the previous one. You have to have Houdini 16. And come on. Yeah, here I have this already. So you see here I have the open color IO option, and I can turn it off, and or I can enable it and say raw, and this will show me the image in linear space, the original render in linear space. If I want to turn this off, I have to disable the open color IO option and then change it to gamma. And now we're back to default. This is how the render looks like in an sRGB space, the same render. And look at these guys. Now to turn it back on, right click and say open color IO profile, and then make sure enable open color IO profile is turned on. And this is set to sRGB. Look how beautiful that is. Now these are the primary options, and if we go under Arnold, I have made a couple of changes to the UI because it's too much dark gray for me. And so if we go here, I'm gonna hit tab and type in Arnold. Now Arnold has great support for OpenImageIO, and they're still working on it. The reason I'm calling it OpenImageIO because that's what the project is, and then part of it is the Asus workflow. And then here, if we go under Properties System, there's this option for rendering. And what this is going to do is when you have values, let's say a shading value, for example, a refraction or absorption, the values that you need to put in, especially with hair, the melanin value for the hair, for example, the value that you're going to put in the shader needs to go through a Asus workflow multiplication to give you the right value, so that what you see is what you get in the render. And to get that working properly, if you click here, you'll see all the options available because of that OCIO workflow that we exported. And the one we're interested in is Asus CG. I generally set this to both of them, and then that will also be used. No, it won't be used. Yeah, it will be used in the texture conversion as well. So when we create a shader, now create an image. See, it says auto color space here. It will use the settings for from OpenImageIO to do the texture conversion from linear into the OCIO, into the Asus CG workspace, and that will give you the correct texture. So everything is set up. You don't have to worry about anything. And then when we start doing some renders, we'll get to the we'll learn how to view them in Nuke, and then how to save them out as well, because I think that you guys will need this at some point. And then what else? I think that's pretty much it. The only The only option needed is you download this and then export the OCIO environment variable that points to this file. Now, when we go to the render view, there is also this option here. But if we turn it off and say load bake, we can actually load the bake file, which is basically getting loaded, but the system takes care of that. So if you go under the Asus 103, under baked, under Houdini, this is all the LUTs that we need. So we can load one from there directly, and that should give us the same result. And the one we're interested in is sRGB for Asus CG Houdini, and that will be the same as the one we were just loading. And I think that's pretty much it for this video. Thank you for watching, and see you in the next one.